Hi, everyone. We're excited to be here. If you see me, please say hello in the chat. There's usually a delay. We want to make sure that you guys see us. Hello, Kanaka. Oh, hi, Shima. Okay, people can see us, I think. So welcome, everyone. This is session 8 of the Learning Salon. Believe it or not, it's been 2 months. I can't believe it. Hi, Melanie. Hi, Dan. Hi, Sam. Just a reminder, as every time, the Learning Salon is a place where we come together to have conversations at the intersection of biological and artificial learning. We are interested in contentions and bridges between the different approaches to learning. We are interested in dialogue in the spirit of maybe the 19th century salons, where hierarchies are flat, where we are progressive about our values and we respect each other, but we don't shy away from getting deep into a particular topic. Every week we have a guest. The guest usually states their position for 15 minutes, and then we have the opportunity to ask them some questions. And the second hour is the sort of audience, and they can, if they choose so, they will write their questions in the Ask a Question button below the screen, as you can see. So please enter your questions there and vote on each other's questions. We will invite you on screen if you agree when we want to have the Q&A session. Another reminder to please remain respectful to everyone. It's totally okay to disagree, and it's totally okay that there is a strong sort of argument or questioning of another person's assumptions. But we would like to especially sort of encourage everyone, especially when they are on screen, to be mindful of what they are explaining to others and when they are interrupting others. Some of the friends of the salon have noted to us that they notice that sometimes men on screen interrupt women more often, and we want to make sure that we catch those moments and we establish a norm where this doesn't happen, or at least that it's brought up to people's attention so that we are all mindful of each other. Again, in the sort of the tradition of sort of flat hierarchies and discussion, today we have John Langford here, who's in fact my manager at Microsoft Research in New York City. And I'm going to wait for, is John Krakauer needing to reconnect? Jovo, you might need to invite him back.
Okay, I'll kick him out and consider inviting him back.
Okay, so I'll introduce John Langford while we're doing this. A gentle reminder to everyone, if you're a junior person, please feel free to ask your questions. For clarification question, there will be a lot of things that John might say that many of us might not know exactly what it means. Ask your clarification questions in the chat. If someone can, they will answer you. If they cannot answer you, we will ask John Langford for further explanation. So don't shy away. There are no questions that are, trivial. You can ask basically any clarification question. As usual, Kanaka, and today, sadly, Brad is not with us today, but he's going to probably join us another time. Kanaka is going to be our moderator, as well as Claire, as well as Eva. And we see you, Sean. Hi. And so just feel free to ask some of your questions there. For broader questions, please remember to vote on each other's questions, because that will help us figure out which questions should be on screen. Did you want to say something, or John Krakauer?
No, I can you hear me?
Yes.
Yep.
So I think my job is, as the by far the least qualified to understand what you're about to talk about, to try and ask questions last so that I can take the role of the audience that isn't familiar with some of these areas. And so forgive me if I ask something blatantly obvious. It's for everyone.
All right, so thank you, John, for that. I think that a lot of us would appreciate it. So I just want to introduce John briefly, unless Jovo, did you want to add something before we?
No, I think that was great. I agree with everything I just said and part of what John said.
again, in the tradition of the salons of the past centuries, we try to be also entertaining at times. Okay, so John Langford is a computer scientist who works in machine learning, learning theory, and in reinforcement learning. You might know some of his contributions, for instance, in terms of isomap embedding algorithms from the year 2000. That was a paper with Josh Tenenbaum, a name that is more familiar to the audience of the Salon. The CAPTCHA challenge, cover trees, and that were used for nearest neighbor search. Contextual bandits, which is a term he coined. So if you've heard that term, this is a term that is coined by John for reinforcement learning applications, learning reductions, etc. He also has a very fun blog that I was told about before I was interviewing at Microsoft Research, hunch.net, and he was the principal developer of VowPal Wabbit, or VW, which is a programming language. And he has been at Microsoft Research for a while now, but before that, he was at Yahoo Research, Toyota Technological Institute of Chicago, IBM's Watson Research. He has studied physics and computer science at Caltech, and then later he got his PhD at Carnegie Mellon. Okay, I said boring things. He's also the president of ICML, the International Conference for Machine Learning, and a very long horizon leader, I would say. I think my favorite thing about talking to John is that he appreciates speculative ideas a lot, and he appreciates thinks in terms of what would make sense in 5 to 10 years. And I think that that's a very good way of thinking about science sometimes. And I think that working with within the short time that I've worked with John, one thing that I've learned is that there's a lot to be done with thinking even in the field of computer science before coding, and I really appreciate that. That's the sort of the thinking first approach. I really appreciate that. All right, without further ado, take it away, John, please.
Thank you. Greatly looking forward to questions. As far as appreciating interesting ideas, I think I credit this to science fiction. I read a large amount of science fiction as a child, and yeah, you learn to appreciate new ideas there. All right, so I'm going to share a few slides and go through them just to start the conversation, and then I'm really looking forward to questions of various sorts. Let's see. We'll go. Okay, is the slides visible? Do you see the slide? Excellent. Yep. Okay. So this is about ground-up intelligence. I guess what I found is that as a person working on machine learning, I have to have an opinion about how to solve AI. And this is partly about that. It's about how we should think about discovering intelligence. Now, obviously, we have intelligence in the sense that people are around and they are intelligent, but nevertheless, you might want to discover the principles of intelligence and think about making intelligent machines and things like that. And I like to think about an analogy when I'm trying to come up with a path to discover intelligence. Right? So, well, we're getting ahead of ourselves. Let's just first consider. So, AI has been a field of research for like 60 years, as far as I can tell. This is well before my time. And there have been some great accomplishments. So OpenAI had this dexterous hand that could manipulate a Rubik's Cube in order to solve it. And, it's kind of impressive. We haven't seen a machine do that before. It's really cool. But at the same time, this is my daughter, and I gave her the same task, and she could do it. Furthermore, her hand is smaller relative to the Rubik's Cube, and so mechanically, it's more difficult for her to do it. So she can rotate the sides and edges of the Rubik's Cube as well as the robot, and now you can compare the amount of experience involved for learning the how to manipulate the robotic hand, there was 13,000 years of simulation time used. Now, my daughter's not very old, and so the amount of time that she could have spent learning how to manipulate her hand is maybe like a year. After you think about, she gets to sleep and she does other things, she talks and she eats and all that. So the disparity here in efficiency of learning is pretty jaw-dropping if you think about it. And this is after 60 years of research into what is intelligence. So there are many other areas where research has done great things. So for example, if you look at the efficiency of solar panels and compare them to plants, solar panels are actually a fair bit better than plants, right? And if you look in like the strength of materials that we can create through manufacturing processes, much better than what we see in the world in many situations. But in terms of intelligence, this is not true. And that's not true in an extremely resistant way after many decades of research with very large investments. I understand that before I really got into the field in the 80s, there was actually a huge bubble in AI that collapsed because it just was not paying off well enough, right? And so I think we need to kind of come at the idea of understanding intelligence in a pretty humble way. We need to understand what has worked and what has not worked. There are many things which are sort of artifacts of past approaches, non-monotonic logic, SOAR, psych, that have not really succeeded. And when I try to think about why they didn't succeed and what has succeeded, I think about ground-up intelligence. So you have seen videos, I assume, of time-lapse building of a house, right? And as you go through that time-lapse video, you start with the foundations, you build the foundations up, you build on top of that, you build on top of that, and so forth. And so many of these other research projects which did not succeed, I think of them as sort of starting with the roof, without kind of regard for how it's going to connect into the foundations. And you can do that in a speculative way, and maybe it'll succeed, but it is a little scary, I guess, would be one way of saying it, to start with the roof or start with something that you know must be a part of intelligence without understanding how it's going to connect. And then does it connect after you figure out how to create an ontology like psych does? Does it connect into machine learning? It's not super clear it does. And so I think this is one of the ways that 60 years of research into artificial intelligence has not succeeded. We haven't tried to build the foundations systematically. Okay, so now if we want to think about the foundations, the systematic foundations, the question is, what is the foundation of intelligence? So I would say it's actually reinforcement learning, right? So in reinforcement learning, you have some observation coming from an environment, comes into an agent, which could be a learning algorithm or it could be a person, either way. You have some policy, some way they're going to respond based upon these observations, and they choose some action, and then the environment later gives them a reward. And their goal is to discover how to maximize the sum of rewards over time. Okay, so this may seem straightforward, but I think there's a very important question to ask here, which is there some more primitive foundation to learning available? And certainly there are other kinds of learning which are available in practice. So the most common kind of learning which is used in practice is supervised learning. But I think there's a great science fiction book to write about a culture where nobody can ever learn anything new. They can only just kind of create examples of what they know. And then over time, the culture just loses a little bit here and a little bit there and a little bit there. And through copy errors, it just ceases to function as intelligent culture. So that's the problem with supervised learning. In supervised learning, you need somebody to provide advice about what the label is for an individual example. So you're relying upon human intelligence to do supervised learning, while reinforcement learning provides a foundation to grow intelligence from something that didn't have intelligence before. Okay, so why will this approach work? And I think the key observation is that it's already been done. Somehow, evolution has already managed to create intelligence. And so we at least have an existence proof that it's possible to build things from simpler to more complex in order to discover intelligence. Okay, so Paul gave an interesting Salon 2 Fridays ago about this. I have a much more cartoonish notion of this. So I think you should refer to his for details, but for the cartoon version, I think of sort of worm level intelligence as being able to seek and avoid things. You can learn to seek and avoid. I think of hunting spiders as having a substantially improved degree of intelligence. They have eyes, they're rich sensors, they can plan effectively how they're going to traverse some terrain and so forth. Beyond that, you have things like elephants or wolves, which cooperate together and have a large memory of some sort. And then beyond that, this is my youngest daughter, and compared to GPT-3, I'm sure she has a terrible log loss. But so there's something that's really there in terms of communicating with her in a way which isn't there when you just play with a language model. So that is a fundamental indication of intelligence that that I don't know how to express very well, but which seems to be beyond whatever we have encountered in animals. All right, so next question is, where are we at in ground-up intelligence? Now, I would break these down into kind of 4 different categories. One of them is basic reinforcement learning. So the simplest form of reinforcement learning is contextual bandit learning. This is reinforcement learning where you don't care about a long horizon. So you're just trying to optimize the immediate reward. And these days, there's actually a service which allows you to do contextual bandit learning very easily. You can go and create one right now. That's kind of cool. I mean, it's not, on the one hand, it's a very basic form of intelligence. Think of it as your own pet worm. But on the other hand, we can do this. And it's not perfect, but it's getting better. And I think that the worm level of intelligence, if it's not solved, will be solved pretty shortly. It's pretty straightforward to see for the problems that exist, how we might be able to remediate them and fully get there. And then going beyond that, you have sort of more advanced reinforcement learning. There's a lot of work going on around how you do reinforcement learning when you have a rich sensor and you need to do planning and you have a long time horizon and so forth. There are more speculative things which involve cooperation or large memory. And then there's, of course, work towards general intelligence going on. So I wanted to touch on 2 of these. One of these is, let's see if we can get this out of the way. There we go. One of these is research into latent state discovery, which I believe will be very important for really solving advanced reinforcement learning. And the other is, something's not right. Hold on. There we go. The other one is contextual memory trees, which are a learning system that supports having a large memory in an agent. Okay, so I don't want to go into great detail into these because this is really conversation, but I want to give you a hint of what each of these are in order to give you a starting point for these conversations. So when I think about latent state discovery, I think a good example of this is a navigation task. So you have a visual sensor you can see with your eyes. You're in a new house. You need to go find the bathroom, for example, and now you can move forward in the house, or you can turn to the left. You can build up a map of this house, and through that process, end up discovering where the bathroom is. Right. So you have kind of all the key components that you want to address in this example. You have your eyes, you can see, and this house is completely different from any other house that you've been in. You know, it's still, you can generalize somehow to effectively learn how to navigate the house. Furthermore, there's a location that you have in the house, and so you know, you can't go forward and then turn left. You have to either turn left and then go forward, or go forward and then turn right. There are choices that you make. There's a fundamental state, and that state is going to influence what actions make sense in the future. And then you also need to explore effectively, right? So maybe the house, that the bathroom is upstairs, and you wouldn't get there by just walking around randomly, because you tend to go down the stairs rather than up the stairs. So these are all the key problems that you want to be able to solve when you're doing latent state discovery. And we had a paper recently. This was at ICML in 2020, but it has a kind of a really interesting observation, which is that if you take your sequences of experience, you build a prediction of whether an observation, action, next observation, triple comes from your sequences, or whether you swapped in a different next observation. So if you can predict whether or not it's observed or swapped in, then you can discover the latent state. And then you can systematically explore the house. And then you can find the bathroom and succeed. So this ability to discover the latent space, to discover the core simplicity of the world, which is the dynamics of the world, seems to be very key in terms of allowing us to build models of the world which are simple and parsimonious, which effectively allow us to explore, discover, and accomplish whatever we want to do in the world. Okay, so that's one of the two things I wanted to mention. There's some other state-making predictions and settings which are in some other papers, but I don't want to go into those. I also wanted to discuss the connectional memory tree. So this is something that is a tree in which you can insert memories and you can query memories. And I think going through the algorithms is a little bit beside the point here, but I want to go through the description, which is that it's incremental. So every operation, so every query and every insertion and every learning operation operates event by event. So it's an incremental system. It does learning. So I think many people are familiar with metric trees, like the cover tree, which I worked on previously. The idea there is that you have some metric which is given to you in advance, and then you're going to organize things so that you can kind of query for the nearest neighbor in the metric space efficiently. Here we have no metric. All that we have is essentially classifiers which predict should you go left or right down the tree. And based upon the experience that we get, and we're going to be able to learn either in an unsupervised way or in a reinforcement learning way. You can do this all in logarithmic time. So it's very important. And it's kind of a strong notion of logarithmic time. So every operation takes time, which is logarithmic the number of memories. contextual memory tree returns memory. So you insert memories, and those get returned when you query things. So this is unlike existing learning algorithms like decision trees, which just return, for example, a class. Here we're actually returning a full memory. So that opens up the range of applications. And then it does indexing. And what I mean by indexing is that there's several different ways to do something which is logarithmic and then not the size of a set. You could just do parallel computation up from the leaf to the root, and that would be logarithmic in the size of the set. This is like a true logarithmic, in the sense that the energy usage, the number of compute operations that you use, is actually logarithmic in the number of memories. So that means that you can afford an effectively infinite size memory in terms of the energy cost and the latency to access things. So it's very different from other kinds of memory that people have played around with. So for example, if you're familiar with something like the neural Turing machine, where they use kind of a soft attention notion of memory, the running time is linear in the number of memories. And so this is in a different regime. It just allows you to access an enormously large number of memories in time which is logarithmic in that number. All right, so this is a data structure, and there's a theorem which is very basic and strong, which says that if your training error is better than 50/50, this is going to be logarithmic time always. So there's a very strong learning theory guarantee. Okay, so I want to finish by just talking about the relationship with neuroscience and ground-up intelligence, because I think there's actually something kind of several nice symmetries going on here. So I'm going to say the hypothesis, which is completely uninformed by actual practice, but which maybe makes sense if you think about how evolution works. And this is the evolutionary efficiency hypothesis that I'm just making up now. The claim is that evolved mechanisms for solving some task are never very bad at solving the task given constraints. And if you think about why, well, it's because if there is an alternative which is much better, then evolution would tend to prefer that substantially. This is not, of course, saying that evolutionary approaches are perfect. They may not be, but they shouldn't be terrible or terribly inefficient at solving things. And maybe this relates to the memory tree in the sense that I believe, without any evidence, that the way long-term memories are stored in a brain must use some sort of indexing structure. Now, this hypothesis happens to align perfectly with amortized algorithm design, which is a technique for designing algorithms from computer science theory. Right, so you want to find an algorithm which is never very bad at a task, basically. So this comes up with search or sorting or many other things. And so there's a nice kind of symmetry between what you might hope to discover in an evolved system and what you might hope to discover in a design system if you're using this amortized algorithm design principle. Right, so then my general understanding here is that neuroscience provides an understanding of the capabilities and the capability order and the elements of how in creating ground-up intelligence, while theory can help us think about the design of robust algorithms and then gives a complementary understanding of how and why and what's possible. Okay, so I have some extra pointers here if anybody's interested. There's some pointers to archive papers about the state discovering predictions. There's the contextual memory tree, and there's the contextual bandits tutorial, which is explaining basic reinforcement learning and how it's practical and in much more depth. There's this personalized service where you can get your own artificial worm, basically, artificial worm level intelligence. There's Vocal Wabbit, which is Ida mentioned earlier, which has many of the algorithms for interactive learning, which we've been working on for quite some time. And of course, we're actually hiring if anybody's interested. All right, thank you. Are there questions?
Thank you, John.
Thank you.
So we've had a lot of chats and questions already in the chat area while you were having a conversation. So I'm going to first invite everyone to sort of thank you for that wonderful introduction of your ideas. And maybe we will start with Jovo and John asking questions, because I feel like today I'm a little bit biased. So maybe I will leave the floor to you guys to ask more questions.
Ida, you're echoing. Did you hear the echoes, or was it just me?
It's just between your ears. Exactly. I didn't hear it, but I'm not that sensitive to it. So, okay. So I'll start. I have a bunch of questions. Actually, let me start by just saying what a big fan I am of your work. And for those people who aren't as familiar with John's work, one thing I've always really appreciated about it is it's very vertical in nature. And so basically my perspective, if he says something, it's definitely worth listening to, because his work spans all the way from having strong theory that justifies the principles of what he's doing, all the way to having actual real world algorithms and implementations that do it. And so, for example, I'm pretty sure, and John can correct the record, when I was using Yahoo Mail, the reason I didn't get spam was because it was using Vocal Wabbit to filter out my spam. Is that true?
It depends on the time, but there were certainly times when VW was used, yeah.
Yeah. So anyway, I thought that was cool. Ida?
One little thing. Where did the name come from? Who came up with it? What's the story of the name?
Yeah. So there's actually several different origins of the name coming together.
Oh yeah, no worries.
So do you know Jabberwocky? The Vorpal sword? And then of course there's Elmer Fudd, who tends to slur his R's. And then the last one is, do you know Monty Python and the Search for the Holy Grail? There's an incredibly funny rabbit in that movie.
I see.
That's good to know. Good historical context.
Yep.
Thanks. So the other thing I'll say is I've been a big fan of trees in general as data structures, not just from a computer science perspective, but also from a statistical perspective, and their abilities to store, retrieve, and operate efficiently. And so John's earlier work on cover trees was really inspirational to me, and I've since been working almost exclusively on trees because I think they're such a beautiful way of thinking about it, and I think they really provide a really elegant algorithm, not just for thinking about algorithms, how memories are stored and how we behave in humans, but also possibly at the implementation level. So with all that said, I have a few questions specifically about what you were just saying. And, one of them starts with the premise of your work, at least as I read it, which was about that reinforcement learning kind of characterizes what we mean when we talk about intelligence in human. And so I think your slide said something like, the goal of reinforcement learning is to find a policy that maximizes the sum of past rewards. And I've been thinking about this a lot recently in the context of this DARPA program on lifelong learning that I've been working on. And so my perspective now is that although most of machine learning really focuses on minimizing the past rewards, in biology, our job is actually to predict how to choose a policy that predicts our ability to minimize future rewards. We don't really care about the past. It's over and we're never going to experience it again. The future, however, we are going to experience, and it's not going to be exactly like the past. So it requires this like temporal extrapolation. And I wonder, just is your perspective that reinforcement learning is solving both of these problems, or we need to modify reinforcement learning to really address the predicting the future rewards?
Yeah, so I guess I think of reinforcement learning as foundational for learning, in the sense that we must address this. We must do reinforcement learning in order to do more advanced forms of learning. So if you think about what people do, like, kids go to class and they're not exactly using reinforcement learning there. There's something else going on in terms of the communication that happens when you have a real language. And so so I think of it as foundational but not characteristic, if that makes sense. Right? So it's something that we need to do. It's the basement, the foundations, and then on top of that, we can think about building up other kinds of intelligence. Okay, so that's one thing. And then in terms of future versus past, there's this notion that comes from supervised learning of generalization. And the idea there is that maybe you will try to learn on past events, but you want to succeed on future events. Now, the notion of generalization, which is used in supervised learning, is not sophisticated enough for reinforcement learning. But that idea of transferring from past events to future events so that you succeed well in the future is, I think, quite important for any kind of success.
And do you think it's in the stuff you're talking about already, or you think we need to advance what you're talking about in order to incorporate that idea?
I think that some of it's there and some of it needs advancing. So a lot of the advanced reinforcement learning that exists assumes essentially a fixed world structure, which you don't know and you discover through experience. But the real world structure is not fixed. The real world structure is changing. And so it's not directly addressed. If we go down to basic reinforcement learning, we encounter these kind of non-stationary world problems all the time, and there are some hacks in the algorithms which allow them to address these situations, even though the algorithms are kind of designed for a fixed world. There's more research going on, which is trying to improve this from a hack to a systematic optimal solution.
Right, yeah, that's helpful. I mean, I've read a little bit about some of the lifelong reinforcement learning work, but I really don't know that literature well, so that was helpful.
Mm-hmm.
The second question I have for you is, you put up this your daughter as like the hierarchy, or like maybe not a hierarchy, but an order of intelligences, and
Mm-hmm.
I'm sure your daughter is brilliant. And there's this idea, the very long-standing idea, that humans are kind of the peak of intelligence. And for me, it feels a lot like things we used to say a few hundred years ago, that humans are the peak of evolution, like we're the best species. And also a lot like what we used to say hundreds of years before that, like the Earth is the center of the universe. And so obviously humans aren't that good at learning lots of things, and computers are. So for example, computers can memorize white noise patterns much more effectively than we can. Computers can do matrix multiplication much faster than I can. They can, the list goes on and on what they're better at. And so I guess the question is, humans have a very particular kind of inductive biases and capabilities that machines don't have, and machines have certain ones that humans don't have. And so what do we do about that? Like, we already have humans. If we want another intelligence that's like a human, just make another human. You did that with your daughter. Now you've got that, right? Maybe we should design machines to complement human intelligence rather than try to replicate human intelligence. Or, I'm not really sure, but it's just, I wanted to hear your thoughts about, should we really be striving for human intelligence, or should we strive for something else with our artificial intelligences?
Yeah, so several points here. One of them is, this is going to sound kind of harsh, but humans are obviously fairly intelligent, but I think we overestimate our intelligence a great deal. Because, for example, I have no idea how to build this laptop, right? It's not humans which are intelligent in some sense, it's civilization which is intelligent. If you took humans and you stuck them somewhere where they were never exposed to language, they would not be able to do anything like what we can do, because we learn in schools and we work together, and working together we accomplish so many things, right? So it's not that it couldn't be. I mean, I do believe that civilization could be recreated if it needed to be, but the process of recreating civilization is not a one generation activity. It is a many generations activity, and it's a many people activity. Right, so that's kind of I think of language as providing some magical ability to leverage each other's intelligence over time, and just in conversations that just many other species just don't have access to in an effective way. Okay, so that's one thing, and then the other thing is, if you, it's kind of implicit in what I was saying, but the amount of intelligence that we have, really just ability to adapt to new situations. Okay, so I certainly agree that computers, for example, are much better than people at many things. But on the other hand, if I try to create an intelligent agent, it's hard to argue that we're beyond the worm stage. And so there's a long ways to go. And I certainly agree that complementing human intelligence in many ways is highly desirable, right? And then in terms of what the goal is in the long run, yeah, it's an interesting question. It is in the long run. Okay, so why? Amongst other things, I also dabble in physics sometimes. And if you dabble in physics, you discover that the distance to the nearest star is actually remarkably far away, right? Many light years away. How are we going to travel to another star? I mean, it's incredibly difficult. It's a lot easier if it's a machine traveling to another star. And so if I want to think about where you would really need something which is fairly intelligent in order to discover new things, actually having a economically viable starship that goes to another star, gets there, builds whatever it needs in order to send a signal back. That's the kind of thing where I think that an AI might really be required in order to even succeed.
I think that sounds like that would be really fun. I'd like to be on that starship. So, I think the questions and your answers are very closely related in the sense that if we're going to try to build AI, we should really know what we're trying to do. And I would just say that humans have this constraint of, our implementation is this mushy pink tissue that is not very precise. And there's all this historical evolutionary baggage that really limits us. And I guess my thought is like, in AI, we don't have those constraints. And humans suck at like temporal discounting kinds of things. We're bad at lots of kinds of learning. And let's not, like, I don't want the goal of AI to be human intelligence. I want it to be much, much bigger. And I don't want it to be general intelligence, because I think that's impossible because of things like the no free lunch theorem and the arbitrary slow convergence theorem. But I want us to be much smarter and kinder and more compassionate than humans. So if we like rebuild civilization, as you suggest, hopefully it'll be a better one that's more inclusive and more fair and more compassionate to everybody. So I think that's all of my questions. I was going to hand it off to John, but John is lost in the woods.
I was going to say this might have been the most sort of the least adversarial conversation we've ever had so far. Agreeing with each other. We coined the term civilization shot learning. And there's a lot of agreement going on. Waiting for John to come and break the peace vibes a little bit.
Well, Melanie asked a couple of really interesting questions, so why don't I invite her on screen?
Awesome. Yeah.
Hopefully she's willing to join.
I'm going to try to call John to see where he is. Oh, can you invite John back in? He's...
Sure. I'll think about it again. John, I don't know how many more invites you get today. Okay. Hi, Melanie.
Hello. I think you're on mute.
Oops.
There you go.
You unmuted yourself and then you muted yourself again, I think. Oh, now you're back.
How's that? Can you hear me?
Yep.
Okay, thank you. This is a great talk. And there's a really interesting conversation off to the side in the chat also. I had one clarification question and one more sort of general question. The clarification question is in these contextual, let's see, I can't remember, the memory trees you were talking about.
Yeah.
What is a memory? And is it real, you know, you're talking about computer memories in some sense, but how is this related to human memory?
Yeah, so a memory here is think of associative memory. So you just have some kind of key value pair, and we're going to want the key to be something that can be input to a learning algorithm, and the value can be anything. It can just be any bit stream as far as the data structure is concerned.
So do you think that's what human memory is too?
I mean, obviously no, in the sense of exactly doing this, but in terms of having a incremental learning logarithmic time indexing system, I wouldn't be surprised if the answer ends up being yes.
Can I want to push back on that a little bit and say that it has to be something like this, right? Like you have to have keys and values that you can retrieve. I think that's just fundamentally what a memory is. So the details we can fight about, but I don't see what memory means if not that, I guess.
Well, the thing that seemed very computerish and not very biological was kind of counting the number of memories and talking about the kind of complexity, you know, time complexity in terms of order, log n or whatever.
Mm-hmm.
I don't, you know, does it even make sense to talk about counting biological systems memories? They're not really discrete things in that sense.
Yeah, so one question I had at one time, we don't have an answer to yet, is how many long-term memories do people actually have? It seems like it's kind of an interesting question. I don't know the answer. I can enumerate long-term memories, but I don't even know how to get a good estimate of the number that I have.
I don't even think it's something you can count exactly, because if I think of memory, you know, it has a whole, it kind of activates a whole set of other concepts I have. And
I'm sympathetic to this. I think it's quite possible that a real biological memory system does things like merge memories that are not in the textual memory tree right now, at least as it was defined, right? So I think there are probably operations that exist biologically that just aren't there in that particular data structure.
let me ask my more general question. So you said you showed a picture of your younger daughter, and you said, you know, communicate. She doesn't have the same like log likelihood loss as GPT-3, but there's something different communicating with her. And I've been playing around with GPT-3s a lot, so that kind of struck me. And you know, I agree with you, but I wanted to get your thoughts on what is that difference, and what's the relevance of reinforcement learning to that difference, if reinforcement learning is kind of the foundation of intelligence?
Yeah, so I don't feel like I fully know the answer to this. So GPT-3 is sort of optimizing log loss in a language model. And that is obviously very powerful when you have a lot of languages you shove into it. If I had to guess, I would guess that there's some real notion of state that people have. And there's a notion of communicating the state when you're using language that is a little bit lost on GPT-3. Right, so okay, so in deep CS theory, there's this notion of interactive proofs, right? And the claim is that interactive proofs are incredibly powerful. You can interactively prove that something is true that you couldn't write like a convincing series of cases for. So that the power of interaction in terms of proving something is very high compared to the power that you might have in just enumerating things. So this is relevant here because GPT-3 is using an enumeration of language in order to build a log model, a model of language. But the ability to interact potentially allows you to go well beyond whatever you could hope to enumerate with the atoms in the universe.
That's interesting. I think GPT-3 has kind of its learning phase where it's optimizing some loss function, but then it has its kind of online phase when it's interacting with people, and it's you're giving it examples and it's completing whatever your prompt was. So I'm wondering if it could get, it's getting its benefit of interaction at that stage. But
so there's certainly benefits of interaction there, no doubt about that. So I haven't played with GPT-3 in great detail, but so some of my more interesting science fiction books that I read in my childhood involved inventing some new language. So if you can try to invent new language with GPT-3, what happens?
Yeah, I don't know.
Well, you can't have a separate learning and evaluation phase, for one.
Yeah, I think that's absolutely key. I mean, that's one of the key things about the difference between your daughter and any kind of machine learning system that we have today, is that your daughter is just continually learning. And at the same time, she's solving problems and so on. So, and we have reinforcement learning, but it's not that still not that continual level of learning, I think.
So the personalized service that I mentioned is doing continual online learning, and that is commercially useful. But again, it's just a simple form. It's basic reinforcement learning. It's just simple, optimized, immediate reward type of reinforcement learning.
Okay, thanks. Do you probably want to bring on Jonathan Flowers now?
Just want to add something to that, Melanie. I think there's a important thing to the question that you asked, which is something that I think I might add to that a little bit, which is what is the connection between these computational models of memory that are developed in the CS or computer science and the computational models of memory together tied with experiments that we have done in the field of human behavior and human memory, some of which have been also validated in some other organisms like rodents, some of which haven't, right? And I think that, Jonathan, thank you. Yeah, I was hearing an echo. So I think that there is a very important amount of work to be done, which is to answer the question that John was asking, for instance, with regards to how much do you store? What is the structure of the memories that you store in each of these kind of computational models that exist? And how many what is the ratio of what you're storing versus what you were experiencing? So am I storing at a one-to-one mapping? That's like the Borges short story that if you start to make a map of the world that is one-to-one and then put it on the world, basically you can't do anything anymore. So it's a little, sounds like it's not efficient. So it must be a little more efficient than that. And so then it's an interesting point to compare the different computational models developed in CS versus developed by human memory researchers, and see which ones are compatible, which ones can draw inspiration to improve one another. I think that your question had it was pointing to a direction that I think is a very interesting direction of research in general. Just wanted to add that. Sorry that I'm not being polemic today. Jonathan, you have the floor. And Melanie, please stay with us. Don't no rush to send you off.
Oh, so John, I had a couple of points of tension here, and to keep with the notion of memory, one of the ways that you described memory was plugging in and out structures of memory, and I don't think fundamentally organisms function that way, right? Our memories are part of the continuity of our experience, and we recall elements of a memory or elements of experience in a situation to be tested out in experience to resolve a problem that we're currently facing. And so there's no real one-to-one correlation. There's merely the ways that we can expand experience to resolve a given problem. Now, the resolution here, and this gets to some of my commentary about reward, the resolution to that situation does not always have to be net beneficial, right? Insofar as a fox will chew off its own leg to get out of a trap, it resolves the problematic situation in a way that is not net beneficial or rewarding for it, except insofar as it gets out of the trap, right? So one of the things that I kind of want to push you on is, one, the use of the reward language as a kind of structuring analogy that I believe someone in the chat said it was an artifact of the ways that we talk about this in neuroscience. And I think as an artifact, it fundamentally structures how we approach these things. And two, to keep with Melanie's point, the issue with the ways that you're kind of treating memory, not specifically what is a memory, but the ways in which your slides seem to imply a kind of plug and play model of memories in use, right? So it's not like I reach back into my memory bookshelf and then plug a memory into a situation. I kind of test it out, and the speed at which I test things out varies, right?
So on the continuity of memories, I guess my experience of memories is not continuous. So if I think back to when I was a kid, I would get up in the morning and I would go to the bus stop. And I remember one morning at the bus stop, I stepped on something and it crunched. And I looked down and there was like these wood chips, around the ground. And there was frost that had built up under the wood chips, and I'd never seen that before, so that was kind of cool. But I don't remember what happened afterwards. Presumably, I got on the bus. It's just there's just this piece of memory that I have from my childhood, and I have other pieces of memory. Like, so I remember I remember when I was quite young, and there were stairs in the house, and I would go up the stairs to go and play with the cardboard boxes upstairs. But I was very confused when I was a little bit older because there were no stairs in our house. And then I asked my mother about this, and she says, "Oh, yes, we used to be in a house that had some stairs." So I guess my experience of long-term memory is that there are little snippets of episodes that I have, and they're not. It's not like I can just rewind and go through the day that I had 20 years ago and recall what was going on. So that's one thing. And now, in terms of reward being an artifact, I think there's actually a really important point here, which is so there's basic reinforcement learning, which in my mind provides a foundation to build intelligence of one sort or another. But as we move away from basic reinforcement learning, I think that we we start getting further and further away from reward. So, for example, there's actually a lower bound that Shankar worked on, and some other folks with him, which shows that if you want to optimize reward for a long horizon, and even if it's possible to do it with sort of a linear predictor, it's going to break down because it's sort of these exponentiating over horizon effects, which can, so errors will happen just randomly, and they will exponentiate over the time horizon. And so the way that I know to get around this is to essentially learn the dynamics of the world, and then use your learned dynamics of the world to guide the process of discovering a policy which achieves a long-term reward. And so at this point, you're already kind of stepping away from reward, or rather, you're building on top of reward, right? So that's you're no longer at the foundations, you're building on top of it. You're doing something more complex. And then I'm sorry, I forgot what your third point was.
I actually didn't have a third point. That was merely the thing. And so I think we're talking about memory in two continuous but different contexts, right? I'm talking about the kinds of memory that allow you to be flexible, like the kinds of memory that we're using right now when we recall theoretical concepts and apply them in this novel situation to resolve a problem, and not necessarily the kind of memory you're talking about vis-a-vis the thing that stands out, which I would say is part of your ongoing quality of it, or your ongoing experience. But there's something about the quality of that experience which stands out to you as unique in experience, which you then like hang on to. So I think we're talking about, I don't disagree that memories function in that way, right? Because if they didn't, we wouldn't be able to say, oh, that's a novel thing. But I think we're disagreeing about the ways that memories function in a particular kind of functional sense here, right? The kind of memory that we're relying upon right now to even have this conversation, right? The ways that we take up past experience, apply it to the present for future activities, right? Or future predictions.
So I certainly believe there are many kinds of memory. One of them is, I think, long-term memory of episodes. Actually, Ida's been educating me about kinds of memory. So there's a long-term memory of episodes. There's also kind of a more of an ontological memory, if that makes sense. So a memory of like what words mean. Well, you may not know where you learned what the word meant. Funny story here. I read much more than I talked, and so even after I graduated with a PhD, I was still talking about chairs. Anyways, there's certainly different kinds of memory, and because of that, I'm definitely not trying to assert that all memory is of a particular form. I think there's also like a skill memory, right? So learning to throw a ball or drive or something like that.
Yeah, but and which gets me to a point that I made early on in the chat. The distinction between say GP3 learning and other machine intelligences learning, and your daughter learning or my cat learning, is that GP3 and other machine intelligence don't need to secure something from the environment to maintain their present state of activity, right? They don't need to learn to interact with an environment and recall the results of that interaction to maintain a characteristic pattern of activity in the same way that your daughter or my cat might, right? And so I think one of the things missing from, at least in my view, from your entire worldview is the necessity of transaction with the environment. Even plants do this, right?
So I completely, actually, I agree about the necessity of interaction with the environment. So there is this personalizer service, and if it does not interact with the environment, it will not learn. If you give it faked up information, it will learn faked up things. And there's some lack of intuition which comes from people working on supervised learning around this, right? So and we have to it's kind of an education process, teaching them that no, it really needs to interact. We can't just do something off on the side and be happy with it, because we won't know how it will perform until it's actually making decisions and experiencing the feedback of those decisions in its process of learning. So I definitely agree that the interaction is critical to a lot of the learning here.
Yeah, and so I think that's the thing that I'm kind of pointing to with the kind of deficiency of your model, right? Insofar as, like, even in a ground up situation, right? The ground up starts from the organization of the organism in an environment and how it must transact with that environment to develop the particular kind of intelligence it has, which I think connects to the broader points of why make a human-like intelligent machine in the first place, right? And so I think kind of where my contention here is that even in your ground-up model, there seems to be an absence of consideration of the kinds of entities, the kinds of organisms that develop intelligence and how they develop those intelligences on the basis of the ways they're in their environment, which results in different kinds of intelligences. Because my cat, for example, has no need to develop an automobile because she can run and has 4 legs and can secure things from the environment in different ways, which leads to different deployments of intelligence and so on and so forth. And so this is I think my main contention with the point here, right? We don't think about, or at least in these models, we don't think about the ways that intelligence emerges as a total interaction of an organism with an environment on the basis of how that organism, like, needs to secure something from the environment. And so I go back to, again, GP3 doesn't need to secure something from the environment, right? So if we could create a context where it needed to do so, then we could start, then we might have interesting ground up conversations about intelligence. But as far as I'm concerned, and this goes to Ayako's point, one, we don't have the technical capacity to make a machine that does that, which then we could then colonize, right? Because there's something there.
So but this seems isomorphic to my complaint about supervised learning as a foundation for intelligence. So in supervised learning, you hire somebody to label things, and that you use the labeled information in order to build a function which tries to predict what the human editor would say, and then you try to deploy it in new situations. So it gives you speech recognition or object recognition or all of these, and so what you're doing there is you are taking the editor's knowledge about what is a penguin, and then you're transferring that into the machine through this medium of labeled examples, and then you're trying to deploy the editor's knowledge again. And typically there's some lossage in this process, right? So these are useful tools. This is where a lot of the economic value of machine learning exists right now, but they're not dealing with an environment. So a substantial change in my mind is now we have things like the personalizer service, which do deal with an environment. Now it's not a natural environment. It's not like your cat, and it's nowhere near as intelligent as your cat, but it can do things like, predict which of the top 10 news stories of the day are going to be of most interest to a person, and that creates some value for some people. So that's nice. You can do things like help nudge healthy habits. Do you want to encourage people to walk more, or do you want to tell them that yesterday they walked more? Right, and so there's different ways to craft the message, and those different ways of crafting the message maybe appeal to some people more than others, and so it ends up help supporting healthy habits. And it's only through the interaction process with that person that the system actually learns effectively. So this is a new thing in the world. There are systems which will interactively learn how to act in the world so as to optimize for something.
Can I ask a question? This is something I've always struggled with reinforcement learning versus supervised learning. You know, I totally agree with you that in supervised learning, there's a lot of human intelligence that is being absorbed by the system because of the labels and so on. But in reinforcement learning, it seems like there's also a lot of human intelligence that goes into designing the system, in that at base, at least, you're just telling it what the state structure of the world is, what the state transition structure is, what the reward structure is, what the goal, you know, how is it that, you know, you can really, to what extent are these systems actually kind of learning from the environment as opposed to learning the human intelligence that's gone into sort of factoring the environment for it?
Yeah, so there's actually many different kinds of reinforcement learning, and the answer is going to vary across them quite a bit, right? So AlphaZero is a really nice accomplishment. It's learning how to solve Go from essentially the rules of Go. Now solve is maybe a little bit too strong, but essentially get solve Go. And there's a lot of careful design of the algorithms which execute things as efficiently as possible on an enormous computational infrastructure, right? So I think that in many other of these simulation-based reinforcement learning examples that you see, there's a lot of work that goes into exactly what representation you're going to use, and what's the learning rate schedule, and how do you tune these things, and there's a lot of details there, which maybe not so obvious when you see a really nice video of things working. There are other kinds of reinforcement learning. So if you're doing more basic forms of reinforcement learning, it's not like. So I think of this kind of work as the data science work, by the way. So the data science work is not gone, but you have reasonable defaults that kind of work, and you can often eke out some substantial additional performance if you do the data science work, right? And now that's not as automatic as you would like. Maybe we can make it more automatic in the future, and that's certainly one of the goals that we have in thinking about research projects.
So I just want to say, first of all, I'm quiet today because I want to sort of allow maximal number of people to interact with John. I talked to John Langford a lot. John Krakauer is going to attempt to ask a question without the camera working. So let's hope. John, do you hear us?
Yes, can you hear me?
Yes.
Wonderful. Yes, please go ahead. The floor is yours.
Yeah, John, Melanie has been sort of my representative a little bit, I hope, but I have to tell you, I find these whole conversations a bit confusing. Yeah. Fundamentally, I do, right? It's very interesting. In one of your first slides, you showed a worm, then a jumping spider or a wolf spider, then you showed some wolves, and then you showed some humans. Forgive me but I think you did that, right?
Yeah.
And if I remember correctly, under the human, you had communication and abstraction, and then underneath that, you had, I think you wrote general intelligence.
Yeah.
Right. So but you didn't get there when you were talking about a rich sense of planning in spiders, nor did you have that word when you were talking about cooperation and memory in wolves. And then what you did, if I remember, is you said, I'm going to take some advanced RL, which you already attributed to the spider, and I'm going to take some memory, which I already attributed to the wolves, and I'm going to combine those two, and I'm going to give you latent state discovery and contextual memory trees, right? And it seemed like you had taken them before you got to general intelligence.
Yeah.
Right? So what I just can't get my head around, and I hope Melanie will be an ally here, is that all of this is various forms of procedural learning, right? It's all a form of implicit, algorithmic, iterative, many trials way of doing things. I'll give you an example. HM, when this is the patient who lost his episodic memory, right? In order to get HM to learn simple tasks that could be immediately explained to a healthy person with declarative injections, that's a thing, and you little doodad and you whiz-waz with that thing, he couldn't get those little injections of meaning to instantly short-circuit the procedural system. He had to just learn it through trial and error. He had to be operantly conditioned to learn those doodads. So in a way, this human could only end up converging on good performance through a kind of RL, simple RL kind of approach, versus just saying, that's a whiz-waz in one sentence, and he would immediately know how to do it if he hadn't. So in other words, ever more sophisticated procedural implicit algorithms with some memory attached to give us wolves and spiders. But the declarative shortcut, the semantic, I don't need to proceduralize, is nowhere in sight, right? And it was even implicit to your slide. So why does this elephant in the room never get mentioned? Now Melanie does, but it never comes up. Is it denial? Is it denial? Is it that one day you'll even algorithmically solve the declarative? Am I going mad, or is it eventually going to happen?
So here's my belief. My belief is that evolution took place, and we did build up various kinds of intelligence over time through evolution. And at some point, language happened out of that process. And evolution in doing this never really made big steps, because evolution never makes big steps. And so while there may be a magic button that happens between a wolf and a human, I think that we can get there through a ground-up intelligence.
Right, but there's a category error that you're making. Logically, it seems to me. I have no problem with evolution being a blind watchmaker, and that itself is a kind of procedural algorithm that has parallels with what you're doing to give things better memory and better learning. But it doesn't follow that the thing that is created at the end of this blind watchmaker itself has the characteristics of the blind watchmaker. That's a logical category error. It could end up with new characteristics that were the consequence of a blind watchmaker, but there's nothing to say that it will have the same characteristics of what you're doing right now.
I agree with that.
But it never gets said.
Okay,
why is that?
I certainly agree that computer intelligence may not be like human intelligence in many ways, because it's operating on different hardware. There are different limits. And I mean, this goes back to matrix multiplication, something that computers can just do way better than humans can. I had an advisor in undergrad who could multiply 5 by 5 matrices in his head. It was very impressive, but yeah, not very relevant as a life skill these days.
But you agree then that, I mean, I just want to separate out the sort of faith part, which is because evolution is slow and we're following from the ground up, we too will have a aha moment, whether it's architecture, whether it's algorithm, who knows. But you are agreeing that that the thing that ends up looking like a human, not a wolf, could qualitatively surprise you, right? In other words, it's not necessarily going to be RL at all, right? In other words, it just seems to me that...
So again, I think that RL is a foundation. I don't think that it's the complete story of what we're building. So I think that just like basic reinforcement learning is basic stuff, that's our foundation. On top of that, you know, you have more advanced kinds of reinforcement learning, which are still reinforcement learning in the sense that there's still a reward that you're optimizing, but you have to do a lot more think. You have to do latent state discovery in order to accomplish it. And then there are other faculties of intelligence, like having a big memory,
So okay, you mentioned
being able to
memory.
communicate and so forth, which are not that, I mean, they assist reinforcement learning to some extent, but these are new capabilities which are kind of built on top of them, and which you can think about as how do I describe this? It's just because reinforcement learning gives you a way to learn from knowing nothing and just interacting with your environment doesn't mean that's the only way to learn. So it may very well be the case that, for example, we have language at some point, a language that allows us to describe something. That description can then be compiled somehow into a reinforcement learning problem that inside of the brain can be used to learn how to do something like your HM, right? Or like you're not HM. The HM couldn't do this, right? And so that ability to take something like a description of how to, I have something really fun here. I've never actually made a desktop, but actually made this very recently. A lot of sanding involved. So I've never done this in the past. I had some advice from people over the phone telling me about what I needed to do. I compiled that and I managed to do this without ever experiencing this as skill memory or something like that. So that ability is something which I don't know how to connect to reinforcement learning.
So why?
But I do believe that we will build towards that and we will find the connection.
But so that's exactly. So you can't connect that to reinforcement learning now. You said that, and yet you believe that you will one day.
Yeah.
How is that not just an expression of faith? In other words, is there something about this extra thing that you can say right now makes you believe that it will succumb to an RL framework?
So it's just an observation of evolution. Evolution never makes a big step. And the only grounding we have in learning, the only thing which gives us a foundation for learning is reinforcement learning, as far as I know. So maybe I'm wrong. Maybe there's some other source of learning which is available to us that it's foundational, but I don't see it right now.
Yeah, it's interesting. I hear, just to finish, I find that argument that evolution did it, and that I feel like there's a disconnect between the process of discovery and the form of operation of the asymptotic discovery. In other words, the way the final product works doesn't have to have the same features as the process that built it in the first place. And it seems to me that you're conflating the operation of the final product with the process which led to it in the first place. And it just seems to me that they're not the same thing.
I don't think that's quite correct, because I'm not advocating for an evolutionary algorithms approach to doing things. I think that's enormously wasteful computationally. I guess I'm hoping that we can move much faster by introspecting about how we can accomplish various learning faculties and discovering the right good, or at least good answers, and then compiling them into a platform that becomes increasingly capable of solving various intelligence-related tasks.
John Krakauer, so there was a question that John Langford, since there are 3 Johns on the screen right now, was asking, and he asks, so what is an alternative other learning approach that you think is available to biological creatures that you think is running it in as a foundation, as opposed to, for instance, the RL framework?
Who was that for?
For you.
Yeah, no, I guess what I'm saying is that I just don't think that. I think there's a difference between, if you said that evolution was responsible for the creation of kidneys, and you could talk about the development and the evolution of kidneys and the process to which we have a kidney, that language is of no use whatsoever if you want to know how a kidney works. When you go to medical school and people ask you about how a kidney works, at no point does one talk about evolution or development. Now, maybe one should, because it would enrich the discussion, but you talk about the actual structure that evolution gave us and how it concentrates urine. And the evolutionary story is irrelevant to the actual current performance characteristics. And the same thing, I hate to talk about wings, but bats have wings and birds have wings, and evolution did convergent evolution on those. But the way in which a wing actually works doesn't require any reference to its evolutionary history. It's interesting, but it's not relevant. So I don't understand. So what I would argue to that question is that performance characteristics do not have to share conceptual features with the process that led to the building of those performance characteristics.
If I may just separate two things here, JK, I guess, I don't know how to John Krakauer. So if I may separate two things out, it's one thing if our goal is to, let's say, we are thinking about sort of the studying of kidneys. It's another thing if you're asking, why do you think this particular stem cell approach is going to lead to us growing a kidney sort of artificially, right? So one, you have to explain things about something about the growth process where you can take some cells and why it would lead to kidney, or what to do to those cells, or how to derive it. In the other one, you can just talk about the kidney without having to do anything.
Precisely, and you can talk about the brain like a kidney, and you can talk about the brain like a kidney.
No, but what I'm trying to say is that the point where John was referring to evolution was not about the point of understanding brains. It was the point to answer the question, why do we think an approach that explains sort of ground level intelligence is potentially capable of sort of explaining something at another level? Why would the same framework be able to? This is the point where this analogy would be to growing the kidney as opposed to studying the kidney itself.
But we're trying to understand intelligence, not grow it.
I think in the case of RL, I think Jova wants to say something, but I think in the case of RL, the growing and understanding go together.
But I think that's a fallacy. That's what I'm saying. I think that's a fallacy.
What kind of fallacy?
Because I think it's a constant conflation of it's between performance and learning. They're different things.
I don't think. Sorry, Ida.
Go ahead.
I don't think, John Krakauer, that it has to be that way. I don't think that John Langford's argument depends on this conflation, as you've said. In other words, I think one can argue that we, the artificial intelligence researchers, are playing the role of evolution. And the point is that evolution at some point discovered reinforcement learning. I think that's a relatively safe thing to say. Like, the worm is doing something like that. And evolution built on that to discover cooler stuff like meaning. And we are doing that. And so it's natural to start, like as he was saying, from the foundation. One foundational thing that evolution found is that reinforcement learning is a thing that we can use. And it's one of potentially several tricks that evolution enabled us to identify that gives us all the cognitive capacities that we have. And therefore, building on it is a natural thing to do. I don't know if that captures either what John Langford was saying or addresses John Krakauer's criticism.
Yeah,
but
yeah.
So I agree with what you're saying.
Cool.
So for John Krakauer, I guess I certainly understand how the evolution of a kidney and the function of a kidney are separate things. And I feel like I could have an entirely separate set of lectures about the function of individual pieces of what I talked about here. here, I guess I'm just trying to. So there are in the world many other paths to intelligence that people have proposed, right? And I'm trying to describe what is my path towards intelligence. What do I think is the right way to discover and build intelligence? So, so I guess I agree with the point about kidneys function and evolution being different things, but I do think that research is a journey, and we need to describe how we're doing that journey.
I'm not, of course, adverse to that thing. It's just that I feel like it causes, at least me, conceptual confusion, where the process argument and the journey argument are both couched in RL. Because in the case of the kidney and the evolution of the kidney, the language of the function of the kidney and the language of the evolution can be quite separate. But what seems to be happening to me here is that RL is being used to both explain the function of the kidney and the evolution of the kidney. And it's the fact that we have a faith in the same framework doing both the function of the final product and its evolution that causes me some confusion. Now, it may well be, I think it was Josh that said that you're allowed to use the same language for the function and for the growth. But I'm not convinced by that.
But there's also a difference between the process and the product of RL and the interpretation of what happened in a particular algorithm versus another. I think that the language that we use when we are trying to explain function is more like the interpretation of what happened in an interaction. So the interpretability of the RL representations that are learned, etc., connects things to the functions that you're describing that can be observed experimentally. And the product, which is a particular algorithm, is different from the process, right? So the kidney is a product of some process. So you can talk about the product and you can talk about the function when you're interpreting how that product interacts with the environment. But then you can talk about the process. So it's not the case that RL is used for explaining things. I mean, we use natural language to explain or interpret what's going on, or we use math, right? So I'm a little confused. We've been here before with John Krakauer, where I'm confused about his concern about these two notions. So I hope that we can open it up gradually. I just want to read Jess's question. She's shy to come on stage, but I just want to read her question because it's a question from a perspective of, I think some folks and grad students and postdocs who have seen Jan LeCun's talks may have this question as well. She asks, you propose that reinforcement learning is the foundation of intelligence. This is the opposite of Jan LeCun's cake analogy, where he suggests RL is just the cherry on the cake compared to unsupervised learning, which is the cake, and supervised learning, which is the icing. Because the RL learner receives the sparsest feedback of the three. I'm curious to hear your response to Jan LeCun's cake analogy. That's what Jess says.
Yeah. So one of the things that I've worked on just as a algorithmic development technique is this notion of reductions. And the idea there is that you can take one problem and you can reduce it to other problems. And in doing so, you often end up essentially creating extra prediction problems, or maybe you can think of them as extra labels if you come supervised learning, or extra or alternate rewards. There's various ways to do this. And okay, so what does this mean? What it means is, for the purpose of an agent, I think reinforcement is critical, because unsupervised learning alone is not, I mean, unguided unsupervised learning doesn't really do anything useful in my experience. It has to, you do something useful when you give it at least some guidance of one sort or another. Now, if I didn't go into details about this Homer algorithm, but if I went into details, what you would see is that I'm creating prediction problems. Is this next observation coming from this observation in action, or is it coming from some other sequence? And so you can call that unsupervised learning if you want, because I'm just doing this based upon interactions with the environment. Or you can call it supervised learning because you're controlling the action that's being taken. or you can call it reinforcement learning, because the dynamic model that you're creating is going to allow you to solve for long-term rewards. I think there's I guess what I'm trying to say here is that there's kind of a ontology problem, a semantics problem in comparing Jan LeCun when he talks about reinforcement learning and unsupervised learning and supervised learning versus what I'm talking about here. Right. So I think reinforcement learning provides that foundation, and many of these other capacities are built on top of that foundation in various ways, or enable that foundation to extend to solve a greater set of problems than they could previously. The exact description of whether or not something is unsupervised or supervised or reinforcement learning is something that I think you have to watch very carefully, because some people use a lot of strange, I mean, they call unsupervised things self-supervised things, or they call, or maybe you're coming from the other direction, and this becomes a point of confusion at times.
I'd like to follow up that answer. I mostly agree with what you said, but I think my perspective on Jess's question is that you're both right partially and both wrong in the following sense. Like, as I said before, in reinforcement learning, the classical formulation is minimizing past rewards. And the generalization error, there's not necessarily in reinforcement learning this prediction of the future and trying to minimize future, or trying to maximize future rewards. Sorry, I'm always in loss function land, not reward land. So reinforcement learning misses that, or at least classical reinforcement learning. Supervised learning, as you said, requires a human to tell you the right answer. You need an oracle. That's clearly not what's really happening. And unsupervised learning is totally useless in high dimensions, because there's an infinite way of doing them, and only some of them are useful. So I would say they're all special slices of the more general framework that we have failed to define as a community, which would be able to incorporate all of them as special cases. With that said, reinforcement learning in certain ways is more general than supervised or unsupervised learning, because it's sequential supervised learning sometimes, and sometimes you don't get feedback, and so it's sequential unsupervised learning. But the formulation of the goal is a bit, I think, wrong relative to what we should be doing. I think Conrad has a complementary perspective on this, so I was going to invite him. Is that right? Jonathan has a complimentary perspective?
Yeah, we have the third John has a comment.
Before we get to that, so one of the things that, I mean, and so a couple of things. One, I think both John and John are fundamentally wrong about communication. And this pairs off something Melanie said in chat regarding the declarative statements made by wolves, right? Wolves have declarative statements within their own internal structure, as do cats, as do many other complicated organisms. And the best example one can think of that is not a terrestrial mammal is whale song, right? So this notion that communication, at least human communication, is a thing, or communication in the modes that humans do is a thing unique to humanity, I think is wrong, right? There's no point where there's wolf communication, then there's this big jump to human communication. You have parallel organic pressures which develop communication differently, or communication technologies, if we want to use technology in the broadest sense of the term, right? Same thing with bird song, same thing with the pheromonic communication of ants and other insects, right? The way we're using communication here, I think, is fundamentally problematic. But putting that aside,
well, just 1 second, Jonathan.
I agree with that.
1 second, Jonathan. Actually, that I do not agree with. It's actually incorrect. In other words, there's a lot of debate over whether non-human animals do declarative communication. Now, we don't want to go into that, but it's actually something that is greatly looked at, which is, are they making indicative versus declarative communication? Communication and its declarative content is something hugely investigated right now in the animal behavior world. And it's not just a given at all, right? And now we don't have to go off on that tangent, but it's actually a very interesting debate, and it is extremely controversial in the animal literature whether they do declarative communication. So it's not just yes, it's obvious. It isn't actually, but we can talk about that another time.
And that's fair. And I mean, I'm fairly clear about which side of that debate I'm on here. But the other thing here, and before I usher myself off screen, is when we're talking about reinforcement learning, right? Nobody ever asks who's doing the reinforcing. Like, this has not come up in the conversation. It was alluded to in John Langford's conversation about the semantic differences of learning, but nobody ever just outright said it matters who's doing the reinforcing, right? Because unsupervised learning could be reinforcement learning when I learn not to whack my head on my car or on the I-beam of my car when I get into it. Nobody's supervising me except myself and my responses to pain, right? So I think, as my last point, we should really think about who's doing the reinforcement in reinforcement learning, because oftentimes many of the things we learn are learned without supervision, right? We're doing the reinforcement. So, and I will usher myself off screen now.
Yeah. So I just wanted to add about the point about communication. The wording is inexact on the slide because there isn't very much there. I actually do believe that animals communicate in even in a declarative sense. I've read various things which suggest this is true. I can understand people debating it, but I think that advanced animals do actually do this, and even create new atomic signals to signal important things in their environment. But what I meant in that slide is more like advanced language, where you have a combinatorial structure from which you can, create civilization.
And I think the point that John Langford just made is the point that obviously cognitive scientists among you would know very well, that unless something has compositionality and systematicity, we don't call it language. And animals at best can do atomic sorts of calls, for instance, etc. But this kind of a grammar that's transferable and generalizable, we haven't observed it in animals yet in that sense. So, okay, Conrad, we're happy to have you on stage. We don't know where your hair is, but you look great.
Great to have me. Hey, so I just wanted to start with a little roundabout way I disagree with Jan Le Kun's analogy. And in a way, I think he has the wrong sense of what matter is. What's the cake? What's the stuff that's delicious? So arguably, you can say the world has two levels. Like, there is this low-level stuff of stuff having visual properties and pixels and it being very, very high-dimensional. And Jan Le Kun is absolutely right that like all the billion ways how dogs can look like you can never learn through like reinforcement learning. But that's just because he's counting bits, which is just so ridiculously boring. On top of this world, there is like this abstraction on which we operate, where things have causal influences of one another. Now we have a light switch somewhere that I would like to switch right now because I don't like the way my face is illuminated here. Of these variables that I can actually do something about, they live in a very, very low dimensional space. In fact, there's a very small number of them. And in that sense, the fact that Jan Le Kun sees the big cake, which is all these bits that are basically just used for this pre-processing, is like really boring, because the interesting stuff, in fact, is to large parts of the reinforcement learning level. And when I say reinforcement level, I of course mean causal inference, but there's almost the same. I need to go to the world. I need to try if that switch actually works. Only then I can figure out that that is what I want to switch at this time. And the one thing I should do is thank my son, Leo, who just came in here, for making me a super delicious look. Like, my son, 11-year-old, already makes like super awesome lattes for me. In any case, sorry for this little expression of love. He's 12, actually.
That's awesome. Conrad, in Snoopy, there's a person that speaks and you just hear like causality, causality. That's what sometimes you remind me of.
Well, you just need to get used to that concept. You will feel better if you start building it into all your models. And in fact, like this way of thinking about it, let me try and link that to how I'm thinking about memories, which might be different to a lot of people in reinforcement learning thing. Now, like for a lot of people in reinforcement learning, memory is just something that you're building. Not like I give it memory at some level. I make some stuff recurrent. I give it LSTMs, whatever it is that I do there. But in reality, for us humans, a lot of it is actually about using memory as a tool. Now, I can say, oh, I talked with John in the past. Let me think of John. Can I like build like can I pull up a John simulation? And either I can or I can't. But if I can, I will be told, yes, you can, and here it is. Or alternatively, it will be like, yeah, actually, like your John simulation isn't worthy to pull him into your like simulator. So there is this level of which, at which level memories, different kinds of memory systems are like really like tools, and they have we can imbue them with teleological meaning, where it's like a given system allows me to solve a certain kind of problem. And as such, it's like I use a tool the same way I use like a pencil or something. I want to like make this painting behind Josh be moving. We can all do that. Not like I can like look at the painting behind Josh. It's beautiful. You can all imagine that it comes to life and starts like hugging him and stuff. It would be very disturbing, but we can all do that. And in that sense, I think that the notion that we have of memory isn't nearly enough.
I agree. I think memory is just one piece of things.
It's a really good point, Conrad. And I would say, although I was making fun of you, your insistence on us remembering causality whenever we talk has been really helpful to me personally. And I think, it's a really good thing to remind us of that when we're trying to memorize stuff, it's because we're going to try to use it later. It's the tool, it's not the goal.
That's right, and causality is a tool, and we make a big mistake if we ignore that, even when we just care about building reinforcement learning systems that work. It's like there are certain things that you can do this to the world, and certain other things that you cannot do to the world, and it's very important to know the difference between the two.
So you might be particularly interested in the Homer part of what I was discussing, in the sense that it is a tool for discovering causality, or the causal structure of the world, which works with generalization. So you never see the same thing twice, and yet still you can infer the causal structure of the world.
Right, and that causal structure also promises to allow us in a way to do certain things that matter for this lifelong learning thing. Like if I really understand the world in terms of what components of the world do to one another, those will much more survive like the change to the future world than like random associations between variables.
Yeah.
But in that sense, I'm sorry, I don't disagree with any of you guys. But like,
we can disagree. I'll bring something up. So, the thing Conrad likes to say causality, as you all know, but another thing he often likes to say is inductive biases. And before he started saying causality all the time, he said inductive biases a lot. And this came up, Jonathan Flowers made a face at one point when John Langford said something like learning from nothing. And I think Conrad mentioned in the Slack too that humans and biological entities, we're not learning from nothing. We are learning from a genetic program that has coded in the developmental plan for the brain and the rest of it. And that's not explicitly in your thing, as far as I can tell. And so I'm curious what you have to say about that, because it seems like we really need it.
Yeah, so evolution is, in truth, another foundation for learning, if we want to think about it that way. And that definitely creates the structure around which agents end up using reinforcement learning. So that's definitely true. I guess I find evolution to be an incredibly inefficient process. And so I'm hoping that by thinking about the design principles and considering how to make algorithms and considering how to grow from, I want to shortcut the evolutionary part of this, because if we wait for evolution, I had a professor once who was into artificial life, and it was kind of fascinating as a subject, but it never went anywhere.
So why do you say that evolution is so bad? So there are scenarios where basically evolution is proportional in speed to the population size or the length of your genome or whatever is the longest of them. And in the end, it seems like a perfectly fast learning algorithm to it. And I don't think we nearly understand how evolution actually works.
Yeah, so if I think about trying to do even supervised learning with evolutionary techniques in, you know, like suppose you want to do an object recognizer. So you have, you know, a few million parameters. If I try to do this in a purely evolutionary process, it just, I think it doesn't really work. It takes forever.
But that's because you pay extra because you run on actual computers for the population size. If you had like, if we talk about bacteria, which might be where much of evolution happened, you might have a population size of 10 to the 20 or something. That's an awful lot of compute if you think about it like that.
Yeah, but it's not compute that I have any control over. So I think that if I'm trying to design learning algorithms, I really want to consider the kind of compute that I can actually use and control in various ways.
Here's why I think John's right fundamentally about evolution being a bad learning algorithm. It's because it's not one. Learning algorithms, typically, you have a loss function or a reward function or some risk functional, and you try to achieve the minimal or the maximal. That's not what's happening in evolution. Evolution, basically, there's fitness forces that kill off bad things, but there's no goal. You don't get to be the best species. You just get to be alive still, right? So it's not actually learning in the same way that we have. It's just not trying to do that.
In that sense, yes. But like the question is, if we want to say describe, how can humans be intelligent? There is like, to me at least, there's a point behind it, which is how much information can we have soaked up about the kinds of ways of thinking that are useful in this universe. And there it matters supremely if we should, not like you can say, at least locally, the environment in which it's optimized is stable. Not like humans got together into little clans, and arguably we're still little clans, and like all us jointly in our audience are like a little clan that feels very different about other clans. That's all still there. And so we can argue that like locally, if you look at evolution, it acts very much like a learning algorithm, and globally, it does not. Not like, because of course, like the evolution of every being affects the evolutionary path of every other. But the underlying question is, at some level, what is the amount of information that evolution can realistically soak up over time? And arguably, I would argue that it's a lot. And I want to just plug something here. In David Mackay's book, Bayesian Inference and Information Theory, there is a wonderful article a wonderful chapter trying to estimate the amount of information that systems like evolution can obtain over time. And it turns out that details of how evolution unfolds matter hugely, like asexual reproduction, where you basically only have one parent, gives you much less information per generation than if basically beings come together and mix, however they do that. And in at least from these back of the envelope calculations, now you can disagree with all kinds of assumptions, a very simple model, but in those views, it's really possible that we contain an awful lot of information about what kind of thoughts are useful and which ones are not.
So I certainly believe that evolution can accumulate information, and I don't think there's any upper limit on the amount that can be accumulated in that manner. I do think that there's an efficiency issue, particularly for anything on computers. So I've certainly seen evolutionary approaches be useful when your search space is not like a million dimensions, when it's much smaller in various ways. So, and I think for many for many individual applications of supervised learning, it's kind of useful to even use evolution for like which hyperparameters do you use for your learning algorithm, or at least potentially useful in that way.
I think I've been unclear, and we came back to the same point twice. there is the question to which level are evolutionary algorithms useful if we want to build systems. And John, I'm 100% with you.
Yeah.
Totally dead in the water because we can construct much better algorithms. But the other question that plays into the intelligence discussion is, to which level should we assume that biology had the chance to soak up a lot of information about the environment? And that is, to me, a very different question. And so I argue that on the latter part, like, we can know a lot about what makes human thought intelligent, and we can have really rich inductive biases, but I'm totally with you that I wouldn't dream of building it into a computer algorithm if I needed it.
So there's kind of a funny thing that you notice when you look at evolution in biology. It seems like there's an unlearning process which has occurred. So there are some animals which, when they're born, can immediately locomote effectively, right? That's not at all what a baby is like, right? So somehow there's the system has shifted a bit from evolutionary learning to some sort of neural learning, because and that means that the babies start in a more primitive state for more advanced species, which is sort of a little unintuitive, and yet somehow that seems to be where the evolutionally preferred outcome, right?
But the question is, what happened? Now, like, there is one view where humans went from general purpose, from specialized systems that learn over evolutionary timescales and turned into ones that learn during their lifetime. But there's another way of thinking about it, is evolution stopped of like overly obsessing about what it builds in when we are born, and started to like put lots of intelligence about like the learning rules and how they and what they optimize and the architecture and all the thoughts that are good and the thoughts that are not good, and kind of like basically move from specifying the rules of how we act to specifying the rules of how we learn to act. And if that view is right, then we might expect the learning rules implemented in the brain to be remarkably complicated.
Yeah, so maybe one way to quantify this is how much of the genome has to do with the neural part of intelligence. Now, I don't know a good answer to that, actually. It'd be interesting to know.
That's a thought. O of 1.
Yeah.
You can't have order operations in things. It's a third. There's no sequence here.
No, but like it. Okay.
Sorry, I just have to interject here because it's 6, and John Langford's daughter has a birthday. Happy birthday. And John, we're very happy that you joined us today. This might have been the least amount of talking that I've ever done on the Salon, partly because I talk to you often, so I wanted to see how others would interact with you. We really appreciate you being here. There was a poll, and we asked people just very recently, so we don't have a lot of votes in yet, but we asked if RL is a good approach to understanding intelligence. And we have so far 30% obviously yes, 60% likely yes, 5.6% no idea, 5.6% probably not. And that actually changed. Likely yes went up. So yeah.
Okay. Thank you. Talk to you later.
Thanks.
That was so much fun. And thanks for organizing this.
Thank you.
Ida, what do we do now? Are we over now?
We can just maybe say goodbye to everyone. John Krakauer, would you like to say something? Bye, Conrad. John Krakauer, are you? I see your icon there. I know you're there, John. Okay.
I just tried to unmute him and failed. I can try to channel my inner John Krakauer, like, you know, Conrad was saying, oh, he's here. I'm doing such a good job. Sounds just like
it's interesting. I just haven't drunk the Kool-Aid. It's really interesting to me that it's very interesting in the history of science, actually, in biology. the functional physiology schools versus the developmental biology schools versus evolutionary schools. And it's really interesting that, and then of course, there's this notion of inferring form from function, function from form. And I'm a big fan of evolutionary thought. I've never been a big developmental neurobiology person, even though when I was an undergrad, I liked it. But I think this confusion of the arguments that one uses to look at developmental processes and evolutionary processes, and that those somehow are going to give us function. Now they may, a lot of people got very upset. They like teleological arguments, and I do too. But I think they're fundamentally different. I don't need to know the history of walls from Sumeria onwards to understand how a wall built in downtown Baltimore is essentially doing its job. The history of wall building and the history of the materials is all very interesting, but it doesn't necessarily factor at all into the explanation of what it's doing. And I find RL is a very slippery customer. It's sometimes about ever advancing formulation of algorithms that can reach intelligence. I think that's Ida's view, that we're going to discover ever more sophisticated algorithms within the RL framework, and that the prefrontal cortex is the ultimate algorithm generation machine, and it will be within the RL framework. Other times I get the idea that it's really how evolution proceeded, and it's how we're going to proceed, and we're going to get there. And I find that those two ways of arguing it are not the same. Maybe I will eventually come around to seeing that they're one and the same thing, but they just don't seem that way to me. And that's what I'd like to talk to John and people like him more, is that it seems like a one-size-fits-all solution that just doesn't sit with me right.
Can you elaborate? Do you think there is a way you can elaborate for us what you think is wrong there?
I think it's the difference between procedural and declarative approaches to understanding the world. HM could end up proceduralizing a process to come to the same place that could be done far more quickly just with a semantic injection. And I'm saying that if we're going to explain the way that HM does it with and without, if reinforcement learning can explain HM before his injury and after his injury, I find it too broad.
Wait a second. That's the strangest thing I've ever heard someone say, because if you have an algorithm, you can do a kind of an ablation study or like lesion your algorithm somewhere and then see what is the outcome on behavior if you lesion it there. If you have a good enough algorithm that has the sort of habit learning and the motor sequence habit learning that's basal ganglia related and has the medial temporal lobe mediated map learning, and you all of a sudden lesion the medial temporal lobe part, you would expect that it will not be able to learn new paths or new maps as HM couldn't, or form long-term memories as he couldn't. But he can learn juggling, for instance, because that's
he can't actually learn juggling. That's actually false. He cannot.
Or whatever it is that you think that
actually, that's exactly what I'm saying, is that, I've written quite a lot about this, is what I'm saying is that all I'm saying is that if it's true that there's a way to construct algorithms in the RL framework, regardless of the very different double dissociated way that patients behave, either it's extremely powerful or it's too vague. And I can't decide which one it is.
So that's what I don't understand, because if you have an algorithm that explains behavior...
Actually, one thing, Malcolm McCarver is saying they can learn towers of Hanoi. Actually, they can't, Malcolm. That's actually been shown to not be the case.
You told me to tell you if you interrupt me. This was an interruption.
Yeah. Right, go ahead. Sorry.
Yeah. So if you have an algorithm and you lesion some part of it, then another part of it, then it should be still able to do some other things. It's not like the Conrad case. John says not true in the chat. What's not true?
You need to finish. I did the wrong thing. I said it verbally and you were correct to tell me off. I should have just written it textually, which I
Right.
did. Right.
What's not true?
That they can learn Tower of Hanoi. That's been re-examined, and it's not the
Oh,
case.
you're responding to someone else. I see. Sorry.
That was before. It was before.
He interrupted you to talk to somebody else entirely.
Yeah,
No,
he
no.
said someone else.
But Ida, are you saying, just so I understand, you're saying that there's an algorithm that's universal and then it's partially broken?
So wait, no, don't. Let's not put words in my mouth. I never said universal. Let's say that you have an algorithm that can learn fast motor sequence learning and has some properties that's like the more long-term memory that needs sort of, let's say, consolidation, or it can learn cognitive maps. And I just lesion the part of it that does the map learning part. Maybe some other parts get somewhat affected too, but it's not going to be entirely failing. That's the point that I'm trying to make.
Right, but it does suggest to me that it's a broken algorithm, right? It's lost a piece of them. It's lost one of the nodes that it has to work with, right? That's the way you're talking about it. I'm talking about a qualitatively different way of doing it, right? When HM tries to learn something new that cannot be assembled like in a Tower of Hanoi task with little bits of declarative memory, you have to fall back on a more operant-like learning process. So in a way, he ends up learning it the way a non-human primate does. And what I'm saying is that the declarative shortcut that can be used so that you don't have to go through that laborious, algorithmic, procedural way of learning it has been removed. And I'm just saying that semantic instructive shortcut to me is qualitatively unrelated to the more algorithmic procedural approach that he has to fall back on when he loses this extra thing. They're just, to me, two completely different ways of solving the same problem.
I'm not sure if you're saying something that negates. Yeah. Jonathan Flowers says he disagrees. Should we invite him? Because like I have difficulty, John Krakauer, I have difficulty understanding. So Jonathan Flowers.
What I'm saying is that there's a way, if you give, they've done this with these patients, right? You give them unusual tools which they have no previous experience with, right? Affordances don't work and previous experience doesn't work. They've been made weird, okay? And you can teach people how to do that. You know, you can say this strange object needs to interact with this strange object, okay? And you just explain it, right? If you give those objects to patients like HM, it's not that they don't have short-term memory. It's just that the meaning that you've transmitted, they can't hold on to. And then the only thing they can do is do lots and lots of trial and error search, and eventually, right? But that is quite different to just going in one sentence. That's how you do it, right? So, and I'm just saying that they're just, to me, two just different ways. One is a kind of bizarre meaning-inflected shortcut, and the other one is more like RL.
So, John, one of the wonderful projects that I'm currently doing at MSR with a couple of folks is this place between NLP and RL. And it's, imagine that you're going around in the world and your ventral temporal cortex is learning some abstractions of the world, like objects, for instance. And then the parts of your brain that process language, somebody comes and teaches you and says, chair, desk, you know, sofa. And gradually that abstract representation in your ventral temporal cortex, which is not linguistic, but it's kind of some kind of an object that you might have acquired, gets bound together. It gets with this sort of linguistic concepts of that somebody told you, somebody taught you, your parent, for instance, taught you. And that binding between a representation that's non-linguistic and a concept that is sort of some notion of concept. It doesn't even need to be linguistic. It is the conceptual abstraction. This binding makes it easier later on for me that without seeing it, you can say the word and I can either imagine it or activate that representation. I think that there's a new, actually very nice review First author is Jay McClellan. It's an opinion piece in Neuron, where he talks about this idea that the sort of future models should bind these two things together, the conceptual part and the representation part. Now you slash in my entire language sort of capacities, if you could do that, which is not something that actually happened in HM, but just like, just because that was the example, the hypothetical example that you gave. Let's say that some damage happens to my brain and I lose language entirely. I still have the representation of the chair, or I have still my basal ganglia loops, supposedly, so I can learn some sequences, I can learn some stimulus response. So the way that I see it, and the way that I see the state of the literature, and the way that I hear your great examples with patients, I feel like maybe we should sit down and compose a list of the patients and cases that you're describing. And then maybe I can see if there is a way to algorithmically design some algorithm that does those tasks, and then we lesion those algorithms and see how they predict, and we can compare different algorithms. I think that's the empirical way to address the claim that you're making. But I think if you're just saying that there is some ghost in the machine, there is some notion of meaning or semantics that's not going to arrive by showing this exercise that I just mentioned, then I wouldn't know what is the empirical way to approach it.
Sure. I mean, that's a great, I completely agree that I guess if it all comes down to what you and I have talked about a lot, which is it the difference in the algorithms that is the most important thing, or is the framework for the generation of all these algorithms what we're arguing about? And I think that if you said, John, there are qualitatively distinct algorithms that can lead to the dissociations you see in patients, but they all can come under the framework of RL, then I would go, okay, I've learned something. The question is what's the superordinate category and what's the subordinate category? And it seems like the superordinate category is RL, and the subordinate category is all the different potential algorithms. And if that's true, then that would be fascinating. I just don't think that RL is a superordinate category.
Jovo, you have a response, it looks like.
Yeah, I mean, I think John and I had a very intimate salon about this earlier this week. And without disclosing too many details about what happened, I could just say that I think John convinced me at the time that basically the fact that RL can do all this stuff, from that, it does not logically follow that it can also do the other stuff. It may do that other stuff where the other stuff is semantic, meaning, etc., and it may not. And he's just pointing out that if you say you think it will, that's a fine thing to say, and you can believe that. And he's saying the proof is in the pudding. And I think Ida's experiment is a beautiful and the first experiment I've ever heard where one could actually test the claims that people in RL are making that this is the way to do it, which is basically what John Langford was just saying. And we can see by doing, I mean, that experiment sounds quite complicated and difficult to implement, but it's at least a start where we can think about really vetting these ideas much more seriously.
I think it's not as difficult as you guys think it is, but it's definitely difficult, and I just dug myself into a hole. Okay, Jonathan Flowers.
So a part of what I'm going to say is in general agreement with Ida and John, but it actually, I think it pushes back against some of John's concerns here, right? Insofar as I don't think we need to think about these categories as superordinate or subordinate. And I think folks who try to make that distinction are, engaging in some problematic metaphysics here, right? We might want to think of these things as continuous, right? Because nobody. So, and I'm gonna think about this in the context of skill development, right? As a motorcyclist, I can tell another motorcyclist the operations for upshifting in a kind of, or changing gears on a motorcycle in a kind of shorthand. But when I'm teaching a student to ride a motorcycle, I can't do that, right? So the kind of shorthand semantic thing that John is talking about is absent because they haven't gone through the algorithmic process, the experiences to develop an understanding of what that shorthand is. So my argument here is that The algorithmic processes that John is talking about are continuous with the shorthand, and you need both. Nobody develops a shorthand prior to going through the algorithmic processes. So to give a broader example, right, if I say kesagiri, right, nobody, unless you've practiced, you know, a particular kind of martial art, understands what I'm saying when I say that. That is a shorthand for a diagonal cut from shoulder to hip. But it also functions in that semantic thing that that John is talking about. But you would not understand what it is unless you went through the algorithmic process of associating, as Ida said, the concept with the algorithms and the stuff and the other kinds of things. So my concern here is that we're engaging in this kind of unproductive dualism when we separate John's shorthand from the algorithmic process. There's no superordinate or subordinate.
I actually disagree with that. Okay. That's very much the sort of, you know, what, you know, going back to the 50s and 60s, Chomsky argued very much against this sort of associative referential theory of words and language, right? And he uses a very good example of the notion of house, right? The notion of house is not just, look, that's a house, call it a house. A house is full of reverberating meanings that go way beyond just that's a house. So in other words, to say that meaning is no more than associatively learning a label between a word and a thing, that's what actually non-human primates can learn. That's why they can use the imperative a lot. Animals can learn associations between an arbitrary gesture and an object. That kind of learning doesn't lead to declaratives. It doesn't lead to what Ida was talking about, the sort of systematicity and compositionality. So that story of just learning an association between algorithmically is precisely what humans do not do. That's the point I'm making.
What I'm saying. I'm not saying that you can reduce one to the other or that one is the other. I'm saying that they are in continuity, right? That we have to go through a process that is in some way algorithmic, in some way, especially if we use algorithmic as a series of steps that lead to a particular way of solving a problem, right? We have to go through an algorithmic process in order to develop the shorthand that cuts that process short. And insofar as we don't, again, we're going to have to, it would be a longer conversation about whether or not animals can do this. But insofar as we have not, and let me put it this way, insofar as we have not observed animals doing this in the ways that humans do, right? I don't think it's safe to say that animals can't or don't. But all this is to say is I'm not saying that we can reduce one to the other, nor that we can reduce meaning to mere association. I'm saying that these are continuous, that there's a continuity between these two. Now, what goes along within that continuity is worthy of further study. But my concern here is, again, that we should not draw this hard line between the human capacity to generate these semantic shortcuts and the algorithmic and what you're describing as the algorithmic learning. I think there's a continuity there that gets us from one to the other, not in identity.
Right. I mean, I think the discrete from the continuous, Jonathan, is always interesting. I mean, I feel that even if one ends up making continuity arguments, in the end, we're going to have some parallel vocabulary to explain the difference. And we know that discrete things can arise out of the continuous. So they both can be true. There can be a continuity evolutionarily, but I do not, again, the sort of the power of the word algorithm, that everything is an algorithm. All I'm saying is that maybe that's true, but it's too meta for me. I need to know, as you just said, what the difference is between the semantic shortcut and the way that poor HM had to do it algorithmically. I need a vocabulary of the difference. And if there is a superordinate algorithmic way of explaining both, like Ida's saying, then I would defer entirely to that. But I would still need a language of the difference as well.
But the whole point is that the algorithm will provide you with a formalization of those differences, because the different components or parts of the algorithm would correspond to each. And this reminds me, maybe we should do like a hackathon together, where I just like live code together a couple of basic algorithms. So you know, and then build up on top of it and build something that has two different components, you know. It can be very simple, but I feel like maybe during that process we can have the discussion, because then I would better understand. Maybe we're not syncing because we're not thinking about the same kind of, maybe this is the future of discussions, like live coding or live.
I mean, you know, there's somebody, maybe Zena, I mean, you know, Zena should come in a minute, actually. We're here. Let him invite, can you invite Zena in a minute, please, Jovo? And keep Jonathan. And keep Jonathan. Yeah. Can you please bring Zena in? He says declarative knowledge is by definition non-algorithmic, and I agree with him.
I'm not talking about declarative knowledge, or I wonder sometimes where we are going with these discussions. I'm talking about a particular behavioral phenomenon you're describing. Please let me finish. And that there could be two different algorithms, two different parts of the algorithm, and you take out one part and it would look like the behavior of the lesion person. I'm not going to get lost in a labyrinth of words and how you would name things and say, but this word doesn't mean, I'm not going to get lost in that. I'm going to stick to what I said from the beginning, specific behaviors, an algorithm that explains specific behaviors, you lesion some part of it, you predict another behavior. Not all algorithms would be able to do that. We need to design one and we need to compare them. Hello, Zena.
Zena, help me, please.
Hi. Nice to meet you. No, so the point that I just made is a fairly straightforward one, which is that there's a difference, you know, in a kind of a technical sense between algorithmic knowledge and declarative knowledge. Declarative statements are things about the world which you think are true. They're statements, and algorithms are procedures. And so all I'm saying, in some sense, I'm agreeing with John, which I think there's different kinds of knowledge. I wouldn't say that there's necessarily a continuity between them. But you know, they're not mutually exclusive. You can use both in different contexts, and you can combine them in different ways.
But they are different, Ida. They are different.
I mean, your backup person also is not backing you up entirely, John. I'm sorry.
Yeah, I would agree that your backup person actually like suits my statement, right? An algorithm is a procedure, right? But you still need a procedure to get to the declaration of knowledge, right? It's called a process of inquiry, at least if we're going to be pragmatic or Deweyan about it, right? You have to run through a process of inquiry to make a declarative statement about the world. And you can you can reduce a process of inquiry to an algorithm, although I'm really hesitant to say that because there are other ways of engaging in inquiry in the world. But let's put that aside. You can reduce a process of inquiry to an algorithm, right? And in fact, most of the algorithms we use commercially automate our processes of inquiry to sell us stuff. Now, what I'm saying here is that you can use an algorithm to get to a declarative statement, and we do that all the time when we figure out what colors are or how to describe a thing, things like that. So all I'm saying is there's a continuity here and not a fundamental or not an identity. And Zena, thank you for actually saying that, because it doesn't like it I think in many ways foregrounds what I've been trying to say here, right? The algorithmic that or at least in the way that we've been using it, is continuous with the declarative, but not identical, right?
Yeah, so I guess from my perspective, the question is, what do you mean by a continuity? Right? Often when you say the term continuity, it's like there's these two things, and there's a continuous line between them. And so maybe I'm in both camps, because I would, on the one hand, I would somewhat disagree that there's a continuity between these kinds of things, but I will accept that there are these two kinds of things, and they are of a different form, and they're both useful. And the hard part, I think, is how do you combine them in different ways? How do I take my, I don't play piano, but suppose that, let's say, I cook a lot, right? And I've gained a lot of procedural knowledge about how to cook, and somebody can come in and say, hey, Zena, actually, when you add salt, you should add twice as much as you usually do. This is an injection of semantic knowledge, as John says. But I can take that fact and I can combine it into my then procedural acts. The only other thing I would say is that I think some of the confusion in this conversation is not making a distinction between knowledge in my head and communication, right? I may have, knowledge about how to act in the world or how things work, but when I communicate that, often I'm making declarative statements. And so I think that the conversation will be a lot more clear if people make the distinction between communication as a verbal act versus the result of that communication.
I'm not sure if it's just that, because having a shortcut for some of the abstractions that I've learned of representations will allow me to reason or make inferences without communicating with anybody else. Just reason or make inferences in the space of those abstract concepts without having to run a lot of simulations on the lower level constantly. So I can think about, so when which corresponds to, for instance, in reinforcement learning, there's the notion of action, which is go left, right. There's a policy, which is a sequence of actions. There's optimal policy, sequence of actions that maximizes reward. But there's the notion of options. And options is the sort of abstraction in hierarchical reinforcement learning. Is an abstraction of policy. So instead of telling me exactly which steps or which sequence of actions will get me outside to the park, it's going to say, get out of your door, go downstairs, take a left, walk until you reach the park, right? So that's a kind of it doesn't specify for me what specific sequence of actions I'm taking. It's a kind of a generalization of the kind of policy that will get me there. And then there's a generalization of that. Now, it's useful sometimes that we will operate only in the space of the higher level abstractions instead of doing all the simulation one step at a time, whether it's for planning or whether if I'm reasoning about, is there a shortcut or not? I could simulate everything. And there are those things that happen in rodents, especially observe the sort of rapid firing of different paths, etc. Or I could reason using a shortcut, and this shortcut could be images, this shortcut could be language. And I have the ability to sort of put them together in different ways. You're right, I could have the ability to also give directions to another person, but in this case, even when I'm not communicating, I can use them as those shortcuts and think in those shortcuts and reimagine them in different ways. Spatial navigation is a tangible example, but if you think about other concepts, like what's written on your shirt, free life, like that's impossible to simulate without having the notion of concepts, right? Even if I didn't want to communicate, if I wanted to just think about it. I hear, is that John's voice I hear?
I just wanted to have one question to Zena. So just so I understand, so you do not think that one has to algorithmically derive declarative knowledge, right?
Yeah, sure. I agree with that.
That one doesn't?
Sorry, what's the name?
I would agree that you do not have to algorithmically derive knowledge, with the exception that often if you're making an inference, there's an algorithmic component to it, right? So, but this is, I think, maybe a slightly different kind of algorithm than the one that we're discussing.
Yeah, we're talking about an algorithm that functions the way that your brain is functioning. And to have knowledge, you need the brain. And to have, the different parts of it would do different tasks. So the part that will make an inference might be different from the part that's learning a representation about a chair. But, and they all work together. So I guess the idea of algorithm is the learning approach or the inference approach or the different components of learning. So I think you're right that we might be talking about different things slightly, but I see your point. I see your earlier point, definitely. John, are you there?
Which John?
Any John at this point?
Oh, well, no. I think it's really, and Zen and I have talked about this, but I do think that whether one ends up having another formulation for how one uses knowledge to make inferences and thinks about that algorithmically, and the inferential process can be simply considered algorithmic in the very word process, sure, I would say, but I don't think that's the same as the kind of more procedural, as Zena put it, way of getting to the answer. And I absolutely agree with you, Jonathan. I've done a lot of work on sort of proceduralization of the declarative. What I've not seen is the proceduralization to get to declarative. I've seen the opposite, that you're declarative and then you automatize it. There's a lot of examples of that. That's how we learn skills in sports. But I just don't understand what it means to algorithmically learn a declarative fact like add more salt, unless we're talking, as Ida just said, a very different notion of algorithm to the one we've been talking about today.
Right. I don't know what you think algorithm means, John Krakauer.
Yeah.
I'm saying it's either a mega notion, right, or it's in the RL framework, which is it's a way of iteratively just learning structure in the world, right? That is what it is, right? It is a iterative procedural process, right? For whether it's as you have talked about, walking around a maze without reward and learning successor representation or learning, but what we're talking about is a one-shot semantic thing which isn't remotely learning or iteratively related.
But it should learn stuff to do it. I'm sorry, you go ahead. You go ahead, Jonathan.
Oh, okay. So a couple of things, right? So you're talking about a one-shot thing that isn't iteratively learned, and I cannot wrap my head around that, because in order to get to Zena's point about this needs salt, the person would have to engage in a limited kind of process of inquiry, and I might be using algorithm and process of inquiry in a very broad sense. They'd have to taste Zena's food and say, hey, that needs more salt. Or they'd have to watch Zena in the process of creating the food and say, hey, you should add some more salt, right? And then you get your declarative, right? So I'm trying to figure out how you can get a declarative statement from, it seems like you're saying they come from the ether, right? I'm trying to figure out where they're coming from, because any declaration I can think of, ouch, that hurts, that needs more salt, that's a red car, et cetera, is the result of some process of inquiry, some transaction with the world that gives, or within a context that allows the declaration to make sense in that world. This is my tension here, right? So either I'm using algorithm in a really expansive way that doesn't match with what you're doing, or something else is going on here.
I think it's just so expansive that it covers everything from what we've been hearing about today to Sherlock Holmes to, I mean, obviously, I just feel like, again, either we have a concept that's so expansive that it dissolves away distinctions, but, you know, where I live is where Zena came in saying that procedurally learning to cook and having someone say it needs more salt, those two things to me are fundamentally different.
So then how else would you learn that a thing needs salt if you didn't go through like a procedure of, say, tasting the food, right? Even that as a procedure is like, even though it's a procedure, it's lightning fast, right? And we engage in procedures like this all the time when we walk or when we engage in like motor functions. Like, so yeah.
So if I may add one point, John, it's very simple. Algorithm doesn't need recursion. It's enough to say, step one, take your spoon and try the food. That could be itself like a whole like loop that goes on there. I'm just going to abstract it. Step two, taste it, assess whether the salt level fits with what you have in your memory about what's the right. So you do a pattern matching between the amount of salt and what's in your memory, good salt. Step three, announce it, use communication to express your salt needs to the host and say, hey, I think this needs a little bit more salt. Can I have some salt, right? This is the minimal algorithm that you need in order to express that. So there is an algorithm for the example of salt. And what are you doing? Jovo is moving his head. It's almost like.
So I think, you know, as I said, I talked to John about this for hours earlier this week. And I think he's saying something different than what you guys are arguing. And in particular, he's saying, for Zena, who is cooking, there are two different processes for learning. One process is him trying different flavors and stuff and deciding what tastes good. And there's another process, which is someone just says to Zena, add more salt. And then Zena has learned more salt. But Zena didn't go through a procedure. That other person went through the procedure of trying the salt.
There is no, what is the difference? Like you needed to, okay, the algorithm for somebody telling you, one, listen to the, interrupt me, John. The communication channel input, one, listen to what they say. Don't interrupt them, probably. They say, add more salt. 2, you pick salt because you translate that into some action, some plan of action. I pick salt and I add it. 3, taste it and see if it's right. 4, probably ask them, is it okay now? That's an algorithm too. I don't understand what's going on. If you're Ali Reza Hashemi in the chat is saying maybe he's talking about one-shot versus procedural learning. And if that's the case, then there's algorithms for one-shot learning and for procedural learning. I don't understand what's going on, John.
The word algorithm has become a god, and I don't find it useful.
No, it's not. I don't know what you're meaning.
There's an algorithm for everything.
Could I just jump in quickly? So my original comment, which caused John to bring me in here, is that there is, in my opinion, and many people's opinion, a distinction between declarative knowledge and algorithmic knowledge. Like a declarative knowledge is a statement about the world. So this needs more salt, right? It may be subjective. It requires a knowledge of everybody involved. It requires the models of the world, but it is a kind of in a technical sense, it's a different kind of thing than the procedural knowledge that I use to cook. And so, in this sense, I'm on board with John. I think there is a distinction, and I can be communicated that declarative knowledge and incorporate that into my behavior. Where I was arguing with John, earlier this week was I think he puts too much into this notion of declarativeness. I think there's stuff which it doesn't quite handle, but I am on board with the assertion that there is a fundamental distinction between a declarative statement, which is a fact, which is true or false, and a procedural ability, which is has this algorithmic content.
So it seems to me that you're conflating algorithmic and procedural. The term algorithmic doesn't mean procedural knowledge, right? Procedural knowledge, I agree with you. There's a distinction between procedural knowledge and declarative knowledge. I'm fine with that. There's a difference also in the brain between circuits for procedural memory and declarative memory. So we're all on board with that. But algorithms, in the sense that are used in modeling, it means what is the sort of the steps or the kinds of learning or representation steps that you can design a system that's going to acquire and use declarative knowledge or acquire and use procedural knowledge. That's what the term algorithm means. And that's what it has always meant. So that's why I'm confused where, but I see now where the confusion came from, because you were equating algorithmic with procedural. And they're in terms of...
Can you tell me, because what is the distinction between a procedural process and an algorithmic one? Because I've been looking it up and they both say sequence of steps. So what is the difference? And I'm asking sincerely, because in both cases, they say they're a sequence of steps.
An algorithm, it comes from the word al-Khwarazmi, which is the name of an Iranian mathematician that lived many centuries ago. And Khwarazmi designed this idea for sort of sequential steps to compute something or to solve a problem. And that's, it doesn't have a domain. It can be, it can be the sort of the sequence of steps that you need to take in order to acquire factual knowledge. It doesn't have anything to do with that. The term procedural knowledge and procedural memory, I think probably Talving is one of the people who started to dissociate all these different notions of memory, dissociating working memory, procedural memory, episodic memory. I'm not sure who was the first person who came up with this. If somebody can Google our fact checkers, that would be awesome. I will do it, of course, after I speak. So it's not that I'm giving any task to others, just as a matter of simultaneity. But that's a different notion. That's the idea. And brain-wise, that's the idea that there is a particular kind of sort of knowledge that is like riding a bike, for instance, that relies on different parts of different sort of circuits in the brain, as for instance, long-term memory of where I went to school in high school. And it's something that I learned in motor loops. And for instance, cerebellum is relevant there. If I lose my cerebellum, I would be worse at it because it requires or coordinating certain kinds of sequences, etc. So both neurally and in terms of definitions in psychology and the kinds of experiments that happen, procedural versus sort of declarative are just different types of knowledge or memory, whereas the notion of algorithm is a set of steps that are that offer a particular solution or an approach to do something. For instance, make coffee or write a book or remember my childhood, or just one by one imagine all of the different sort of rooms in my childhood home or something like that. So does that help? Joe, do you want to say something? You look like you want to say something.
I think, so my perspective is what John is saying, something much more banal than your interpretation of what he's saying is, which is that there's different kinds of algorithms in humans that learn different kinds of stuff. And learning like procedural stuff, learning declarative stuff may be a different algorithm. It may be the same algorithm, but it's not obvious to him that one algorithm that does one thing should also be able to do the other thing. And that's an empirical claim, and we can vet it out. Is that right, John?
Yeah, it is. I'm saying that you know, it's interesting actually. Carlotta Pavesi, she's a philosopher at Cornell now. She was at Duke. She's written very beautifully on actually the origins of procedural learning and memory actually coming from the computer science literature, not from biology initially. And it's actually very interesting. I find it quite confusing reading that, you know, talking about procedures and algorithms, very often they sound very, very synonymous to me. But fine. I'm sure that there are fine distinctions where the sequential nature of the two diverges somehow.
It's not fine. That's what I'm trying to understand. Which literature do you have in mind? Which discipline?
I'll send you. It's computer science and from biology. But it's all right. We'll do that offline. I'm just saying that if it turns out that one can take this sequential step notion and it works for declarative knowledge of the kind that Zena talked about, and the sequential steps approach for procedural learning, the way HM learned things because he didn't have declarative knowledge. And if it all can be turned, as you in the chat, turns into a menu of steps, fine. I'm just not currently conceptually empirically convinced.
I'm not sure if that, yeah. I think conceptual confusion and conceptually convinced are different things, but.
My thinking on this, right, when we're thinking about procedures and algorithms, right, I mean, there's two ways we can think about this in terms of terminus, right? An algorithm usually has a defined end, whereas a procedure typically does not, and not in the recursive sense, in that when you run through a procedure, you take up the results of the procedure and then apply it to future applications or future engagements of that procedure. In some senses, there's more of an integration when you run through a process as a procedure being a formalization of a given process, right? So I tend to think about these things in terms of their terminuses and the degree to which the integration of the steps is necessary, right? So I cannot imagine an algorithm where you don't, in both the integration happens differently, right?
Yeah, I agree with you. I just have cognitive dissonance at imagining that one can program in a sequence of steps a declarative fact. To me, that sounds like a contradiction. Now, Zena,
no, I don't think you can do that.
Anyone says, I'm just getting a little confused about why you keep saying this. The point is there's a sequence of steps to acquiring a fact and for internal representation to register or infer or store it. That's the point. That's the algorithm.
But the operation of it is different.
You have different algorithms for procedural knowledge and for declarative knowledge.
I just at the moment don't find that helpful. That's all I'm saying. I'm being honest. I just don't find that helpful as a notion at the moment.
I think you've been using the word so confusedly that I would be surprised if you right now immediately found it helpful, to be honest. I think there needs to be a kind of a, baseline check.
Well, then, I just disagree, right?
No,
I just
not an expert disagreement, but I respect your disagreement.
So
Right.
John, is a recipe an algorithm?
yes,
Is a recipe a procedure?
it is too, right? Yeah.
Is a blueprint an algorithm?
You can learn. You can learn a recipe.
Hold on,
You
John.
could-
Other John was talking. One John.
I mean, I think
interrupted the other John.
I'm at a slight disadvantage because I put my hand up and I'm invisible. So actually, I've been interrupted at least 12 times because no one can see my hand.
Sorry, hand being interrupted versus language being interrupted are different things. I think you verbally interrupted Jonathan Flowers after one sentence. So continue, Jonathan.
So my whole question here is, a recipe is an algorithm and it's also a procedure. So is the action of cooking an algorithm, or is that a procedure?
Well, you can procedurally learn or declaratively learn the recipe, right? In other words, you could probably operantly train HM to cook a pasta dish. He could procedurally learn that recipe, or you could just tell him that recipe. So I agree that that's why that distinction has been made in biology versus more generally, as Ida says. But all I'm saying is that I don't think that when you tell him the recipe and he goes, right, I know, I have to do X first, Y second, he's declaratively understood the recipe, which is itself algorithmic, but his understanding of it wasn't itself algorithmic. That's what I'm saying. He just went, I get it. I know what I have to do. Right? Okay. And that's not the same. That moment of I get it, I see what I have to do, is of a recipe, which is an algorithm, but he himself didn't do something algorithmic to go, aha, I see what that recipe is.
Okay, that's where we have the fundamental disagreement. So to understand how to cook is the total integration of this algorithmic procedure for an end, right? If I say I know how to cook this dish, I do not have to engage, or I still have to engage in a process, but I don't have to do it in the kind of mechanical procedural way that you're talking about, right? It emerges as a total integration. And I think that might be kind of cluing in where we're at, right? If I'm getting you correctly.
Yeah, I think so. I think so. It may well be that we'll end up being able to continue with these distinctions as you've just articulated it back at me, and still blanket them with the word algorithm. But I just don't feel the blanketing love right now. But that may be my deficiency.
Yeah, and I think a lot of, and this is more of a cultural point, I think a lot of the ways that we have taken up the language of computer sciences and has obscured some of the larger historical points that Ida has pointed out and others in the chat are pointing out. Even Dewey's notion of habits and processes of inquiry can fall under the modern way of, or the modern understanding of algorithms as this big blanket. Even Mike Annie's definition of algorithms in one of his pieces tends to align with some of this language. So I think what we're running into here is a conceptual entanglement, a result of concept creep. The ways that the understanding of algorithm has spread out like oil over water, such that it becomes really hard to start to disentangle these things unless we decide on a common universe of discourse.
Yeah, I agree. I think I'm a splitter, not a lumper, and I'm just too much of a splitter. But until the lump term does work for me personally, I prefer to stay split. But that may, honestly, and I don't mean this in a deficiency on my part, that I'm a splitter because I don't see the lumping clearly enough. And that's absolutely possible. But I have to talk about splitting and lumping and cooking and recipes. I have to actually have dinner with my friends here. It's now 7. This is the longest session ever.
Closing remarks, and we're so sorry that this was the first time that you arrived on screen, and it was in the middle of this kind of an internal fight. I would love to hear if you have some final words while John's mic is off.
Yeah, well, thanks for having me talk. I think, in my view, a lot of the confusion is because people are overloading this notion of algorithmic, right? And I think there's really 2 different senses. A lot of the ways that John's using it is in literally doing things in the world, right, to achieve some goal. And I think a lot of the ways in which other people are using it is in terms of the processes in your mind. And so I would make this distinction between algorithms in your mind and algorithms in the world. And I think if you make that distinction, a lot of these arguments may actually become non-arguments in the first place.
Could you give us a reference of which text called procedural knowledge and algorithmic knowledge the same?
I didn't claim that.
I see. Okay, sorry. Then
Yeah.
Thank you. Sorry, my understanding then.
So the audience, so the people in the chat, Malcolm McIver needs to come into the room one day. He's been a big fan here, and he's a good friend, and I feel bad that he...
And very good comments too. Very very nice comments.
Yeah.
Absolutely. Yeah. One day we're all going to be in the same room. Okay.
Yeah.
Thank you, everyone. It's 6:52. This is the longest Salon.
Thank you, Anna. Thank you, Jonathan.
Thank you, Jonathan.
Thanks, everybody. Ciao.
Thank you, all the Jonathans. Many Jonathans.
Yeah. Bye.
Bye.
Bye. Good night.